The black hole information paradox. Quantum mechanics has one rule it treats like a religion. Information cannot be destroyed. Every particle, every arrangement of matter, every state that has ever existed leaves a trace somewhere. Burn a book, and the ash still encodes what the book was, at least in principle. Scrambled, yes, completely unreadable in practice, sure. But the information is still there, preserved in the physics of smoke and carbon and scattered heat. Black holes disagree with all of that. When something falls into a black hole, it's gone in a way that feels different from ordinary disappearance. Stephen Hawking showed in 1974 that black holes slowly evaporate through what's now called Hawking radiation. Over an almost impossible stretch of time, a black hole loses mass and eventually vanishes entirely. What it leaves behind is thermal radiation, essentially random heat noise carrying no information about what fell in over its entire lifetime. So imagine an entire library falls into a black hole. Every book, every idea, every arrangement of words that ever mattered. Quantum mechanics insists that information has to survive somewhere. Black hole physics says the radiation coming out the other end is just heat with no memory of what created it. Both of these frameworks are internally correct in their own domains. They simply cannot both be right here, at the same time, about the same event. Hawking spent decades believing information was genuinely lost, which would mean quantum mechanics has a real hole in it. Then he changed his mind in 2004, conceding a bet he had held for 30 years. Most physicists now believe the information somehow escapes, encoded in the Hawking radiation in some way that nobody actually understands yet. The word somehow is carrying an enormous amount of weight in that sentence, and everyone in the field knows it. The holographic principle is one serious attempt at an answer. Maybe the information isn't lost because it was never really inside the black hole to begin with. Maybe everything that falls in gets encoded on the event horizon, the boundary of no return, like a two-dimensional record of a three-dimensional event. Some serious physicists believe this might be literally true rather than just a useful way of thinking about it. But here's the part nobody has actually solved. If the information does escape in the radiation, how does it get out without violating causality or travelling faster than light? Hawking radiation originates just outside the event horizon, not inside it. Nothing from inside can cross outward through that boundary. So the information would have to somehow tunnel out in a way that doesn't break a completely different set of rules just to preserve the first set of rules. That's not a small problem. Imagine designing a system where keeping one promise forces you to break another, and the two promises are both supposed to be unbreakable laws of nature. Physicists have been staring at that problem since 1974. The firewall paradox made it sharper in 2012, suggesting that if information does escape, anything crossing the event horizon should hit a wall of high-energy radiation and be destroyed instantly rather than experiencing a smooth crossing, which contradicts general relativity's prediction that crossing the horizon should feel uneventful. So now there are three frameworks in conflict, not two. General relativity says the crossing is smooth. Quantum mechanics says information must be preserved. The firewall argument says those two things together imply an inferno at the boundary. All three cannot be simultaneously true, and nobody knows which one to give up. 50 years of serious work, and the honest answer is still sitting somewhere at the bottom of something nobody can see into. What happens to the specific, unrepeatable information of you if you fell in? Don Page calculated that if information escapes in the radiation, most of it comes out in the second half of the evaporation. For a stellar mass black hole, that's an almost incomprehensible amount of time into the future. We can't observe a black hole evaporate. We can't check whether the outgoing radiation carries the signal. All of our arguments here are theoretical. Maldaceno's work in the late 1990s offered something closer to a proof, using a mathematical correspondence between a universe with gravity and a lower dimensional one without it. Most physicists found this compelling enough to shift the consensus. Hawking eventually conceded. But compelling and proven are not the same word. The correspondence works in a specific kind of universe that is not the one we actually live in. Whether it applies here is still open. What's most unsettling isn't the complexity. Science is full of complex, unsolved problems. What's unsettling is the structure of the conflict. Both quantum mechanics and general relativity are extraordinarily well-tested theories. Both make predictions confirmed with extraordinary precision, and yet they produce a flat contradiction here, at the edge of a black hole, about something as fundamental as whether information can disappear from the universe. One of them has to be wrong, or incomplete, or pointing at something we don't have the concepts to describe yet. Does something cease to exist when it crosses that line, or is it still there in a form we haven't learned to read? The Swampman Paradox. Imagine a man named Donald walks into a swamp and is struck by lightning and dies. At that exact same moment, a coincidence occurs nearby. A second bolt of lightning strikes a pile of organic matter in that same swamp and rearranges it atom by atom into something that looks exactly like Donald. Same body, same brain structure, same neural configurations that stored everything Donald knew, everyone Donald loved, every memory Donald had accumulated over a lifetime. Swampman, as philosophers call him, walks out of the swamp. He goes home to Donald's house. Donald's family opens the door and sees their person standing there. He speaks to them, recognizes every face, behaves in every way exactly as Donald would have. No test you could run from the outside would distinguish him from Donald. No medical scan, no psychological evaluation, no conversation would reveal any difference at all. So is Swampman Donald? Most people's instinct is no, and that instinct is philosophically interesting. Donald was struck by lightning and died. Something else emerged from that swamp. That something else has all of Donald's properties, but didn't come from Donald's history, didn't develop through Donald's experiences. Paradox, named for the river of forgetfulness in Greek mythology. Souls who drank from the Lethe forgot everything before their next life. Here the erasure is more specific, just the trip itself, but the philosophical problem it creates is the same. If your memories of an experience are erased, did you have the experience? Psychological continuity. Theories of personal identity say that what makes you the same person over time isn't just your body persisting. It's the continuous thread of memories and experiences that connects your present self to your past self. Break that thread and something about personal identity breaks with it. So if the trip was erased, the you that persists through time never went anywhere. Your body made the journey. The you that remembers and continues didn't. Which raises something strange about experiences in general. Imagine you consent before surgery to having all memory of the procedure erased afterward. You wake up in recovery. Did you experience the surgery? Something with your nervous system and your face was under anesthesia. Something that looked exactly like you and responded to stimuli the way you would was there. But the continuity of your experienced self was severed. Whether there was genuine experience happening during that gap, or just biological process with no one home, is a question that remains genuinely open. Anesthesia already pushes toward this territory. Most people under general anesthesia report not just absence of pain, but complete absence of experience. No sense of time passing. No dreams, no waiting. Just a cut from one moment to the next, as if the intervening time never existed. Whether something that deserves to be called experiencing was happening during that gap is something neuroscience has not resolved. We have correlates of consciousness, brain activity that tends to accompany reported experience, but correlates aren't the thing itself. The Lethe Paradox takes this further. It asks whether experience without memory is experience in any meaningful sense, and whether a self that cannot remember being somewhere can be said to have been there. Your answer probably depends on whether you think personal identity is fundamentally about what happens or about what gets recorded, and those two things can come apart. Science can describe what happens in the brain during memory encoding and tell you exactly what fails when encoding doesn't occur. It can trace the neural correlates of the experience while it's happening. What science hasn't resolved is whether an event that leaves no trace in memory happened to you or merely happened in your vicinity, in a body that resembles you, but that the you who continues has no connection to. Somewhere in the past, a version of you might have stood and done something and returned, or not. How would you know? Consider deep sleep, not dreaming sleep, but the dreamless stages where there's no reported inner experience afterward. You spend hours in this state every night. When you wake, you have no experience of having been there, and yet your body was there, your brain was there, biological processes continued uninterrupted. Did you experience deep sleep? Most people would say no, but something that was you, in a physical sense, was there and doing things. The continuity you feel in the morning connecting you to the you from before sleep runs through a gap in subjective experience that was, in some sense, just as complete as Lethe erasure. Personal identity threads through these gaps every night, and we don't think about it because memories connect us to who we were before sleep. Lethe just asks what happens when the thread doesn't connect, when the person after the gap can't reach back to the person before it. Some philosophers have argued that this shows personal identity doesn't require perfect continuity of experience, that we persist through gaps naturally, and the Lethe case is just a more extreme version of the same thing. Others argue the cases are importantly different because in normal sleep, the same biological processes that generate identity continue without interruption, even if conscious experience doesn't. The line between those two positions is thinner than it sounds, and somewhere on the other side of that line is the question of whether you're the same person you were before you fell asleep. In any sense, that's more than a useful convention. What exactly crosses the gap when you wake up? The Polchinski Paradox. Most time travel paradoxes involve human choices. Joseph Polchinski stripped all of that away. No people, no decisions, no free will complicating things, just a billiard ball and a wormhole and pure physics. Imagine a wormhole connecting 2 points in time, exit mouth in the past relative to entrance. A billiard ball rolls in, exits in the past, travels across the table, and hits its earlier self just before the earlier self reaches the entrance, knocking it off course so it never enters. No entry means no exit, means no hit, means it enters after all. Around it goes. Grandfather paradox with no grandfather. No choice, no ambiguity about intention. Just a ball in a geometry of space-time that creates a causal loop. No consistent solution exists inside. When Polchinski published this in 1990, it was something of a provocation. The standard physicist's response to time travel paradoxes was to invoke human choice and free will, to say that somehow you'd always be prevented from killing your grandfather by some twist of circumstance. But balls don't have free will. A ball following the laws of physics in a closed causal loop either enters the wormhole or it doesn't, and both options contradict each other. The physicist Kip Thorne, who had been exploring the physics of traversable wormholes seriously, found this genuinely troubling. His response, developed with colleagues, was to look for self-consistent solutions to the equations, rather than solutions that appeared paradoxical. It turns out that if you do the full calculation, allowing for quantum mechanical uncertainty, in the ball's position, there are consistent solutions. The ball that exits in the past hits the earlier ball at an angle that deflects it just enough to enter the wormhole at a slightly different angle, which means it exits at a slightly different angle, which hits the even earlier ball slightly differently. And so on until a genuinely consistent loop emerges. The ball enters, the ball exits, the ball hits itself in a way that guarantees it enters. No contradiction. But this resolution has its own disturbing quality. What it implies is that if time travel is physically possible, only self-consistent histories can actually occur. The universe somehow selects for closed causal loops that don't create contradictions. Events conspire to prevent contradictory outcomes, which means the future, in some sense, reaches back and constrains the past. Cause and effect are not as one-directional as they appear. Stephen Hawking's response to all of this was his chronology protection conjecture, the idea that the laws of physics conspire to prevent the formation of closed time-like curves in the first place, making time travel fundamentally impossible. Quantum effects at the rim of a wormhole would create a runaway accumulation of energy that destroys the wormhole before it can be used. Nature protects itself from paradox by making the paradox-generating machines impossible to build. It's a tidy resolution, but it's still a conjecture. We don't have a proof. We don't have a complete theory of quantum gravity that would settle the question. Closed time-like curves are allowed by general relativity as solutions to Einstein's equations. Whether quantum mechanics forbids them, permits them, or transforms them into something stranger is a question nobody has answered. Imagine a universe in which the ball does roll into the wormhole. Somewhere in the equations, a self-consistent solution exists. And in that solution, every event from the beginning of the loop onward was always going to happen exactly the way it happened, constrained by the requirement that it be consistent with itself. What does that do to the idea that the future is open? If only self-consistent histories are physically realizable, the set of events that can actually happen is constrained by a global requirement spanning all of time. Every event has to fit a pattern that produces no contradictions anywhere in the loop. Past and future would be locked together. The laws of physics would somehow prevent you from doing the thing that would create a contradiction, even before you tried. You'd be deflected by circumstance into exactly the sequence that keeps the loop consistent. Physicists call this the Novikov self-consistency principle. When they work out the physics carefully, they find that self-consistent solutions genuinely exist in many scenarios. What's missing is a mechanism, a way of understanding how the universe selects for consistency. Hawking's chronology protection conjecture says the universe solves this by not allowing the wormholes in the first place. No wormhole, no paradox, no need for self-consistency to do magical work. Whether that conjecture is correct depends on quantum gravity, which we don't yet have a complete theory of. Either time travel is impossible and nature protects itself by physical law, or it's possible and nature protects itself through a mechanism of self-consistency we don't understand. Either way, the paradox points at something fundamental about causation that remains unresolved. A ball rolls toward a wormhole somewhere in Polchinski's thought experiment. The question of whether it enters has been open for decades. What's the right way to even think about an event whose outcome depends on what it will cause? The Ultraviolet Catastrophe. At the turn of the 20th century, physics produced a prediction so absurd it was given a name that sounds like a disaster movie. Classical physics predicted that a simple furnace glowing with heat should emit infinite energy. Not a lot of energy. Infinite energy concentrated at the ultraviolet end of the spectrum, increasing without bound as wavelength shortened. Obviously, furnaces do not emit infinite energy. If they did, looking at a warm oven would destroy the universe. But the equations said what they said, and for a while nobody knew what was wrong with them. Max Planck solved the problem in 1900, and the solution was so strange he reportedly called it an act of desperation. He proposed that energy isn't emitted continuously, the way classical physics assumed, but in discrete packets he called quanta. Each packet had an energy proportional to the frequency of the radiation. High-frequency radiation required high-energy packets, and at some point the thermal energy available simply wasn't enough to produce even one packet of the highest frequencies. The emission cut off. The catastrophe was avoided. But here's what Planck himself didn't initially believe. He thought quantization was a mathematical trick, a computational convenience that happened to give the right answer, not a real feature of nature. He assumed someone would come along and find a classical explanation that matched his formula. Nobody did. 5 years later, Einstein used quantization to explain the photoelectric effect and won a Nobel Prize for it. Quantization wasn't a trick. Energy really does come in lumps, so the ultraviolet catastrophe reveals something specific and unsettling. Classical physics, built on the assumption that nature is continuous, that things can take any value along a smooth curve, was wrong about something fundamental. Reality is granular at the bottom. Energy, light, matter at the atomic scale, all of it comes in discrete amounts with nothing in between. The smooth, continuous world we experience at human scales is an average of something that is, at its foundation, fundamentally chunky. This isn't just historically interesting. The question of why quantization exists, of why nature should be discrete rather than continuous at the smallest scales, doesn't have a satisfying answer. Quantum mechanics describes the discreteness with extraordinary precision and tells you what it does but not why it's there. We have no deeper explanation for why Planck's constant has the value it has, or why there should be a minimum chunk of action in the first place. Imagine being handed a map that perfectly describes the terrain, but offers no explanation for why the terrain has the shape it does. Quantum mechanics is that map. Every experimental prediction it makes has been confirmed, often to many decimal places. What it doesn't provide is a picture of what's actually happening beneath the formalism, a reason the world is the way it is rather than some other way. The ultraviolet catastrophe was resolved by discovering something strange and then building a framework around the strangeness, rather than explaining it away. Physics moved forward successfully and spectacularly, but the strangeness never really got explained. We just learned to work with it. The equation that would have predicted infinite energy from a warm furnace still lives inside classical physics as a reminder that the most successful frameworks in the history of science can be wrong in ways nobody anticipated, right up until the moment the data forces a reckoning. Why should nature be discrete rather than continuous? And what is discreteness made of? Before 1900, the assumption that nature is continuous felt like common sense. Water flows, light spreads, time passes. None of these seem to come in chunks. Discreteness at the quantum scale still feels counterintuitive, even to physicists who work with it every day. Every interaction you've had with technology that processes information is built on quantum mechanics. Transistors, semiconductors, lasers, all rely on quantization being real. We use the strangeness constantly without resolving it. What the ultraviolet catastrophe revealed is that physics can be deeply wrong in ways that don't appear until you push into a new regime. Classical mechanics worked for centuries. At atomic scales, it failed catastrophically, predicting infinite energy from warm objects. Not a small correction, a fundamental breakdown requiring an entirely new framework. Physicists now face something similar with quantum mechanics and general relativity. Both theories are spectacularly successful in their domains. At the scale of quantum mechanics, general relativity breaks. At the scale of general relativity, quantum mechanics breaks. Somewhere in the gap, presumably at the Planck scale, where quantum effects and gravitational effects become comparable, both frameworks fail, and something new is needed. What that something is, nobody knows. We're somewhere in the period between the ultraviolet catastrophe and the Planck revolution, if there is one. The furnace is warm, the equations say something impossible, and the resolution, whatever it is, will probably be as strange as quantization was in 1900. When the next catastrophe forces a reckoning with what we assumed was continuous, what will the chunks turn out to be? The delayed choice paradox. Quantum mechanics already gives you plenty to be unsettled about. Particles exist in superpositions until measured. They seem to be in multiple places at once until you look. But John Wheeler found a way to make the strangeness specifically stranger by asking what happens when you let a particle travel most of its journey before you decide what kind of measurement to perform. Here's the version he made famous. Light from a distant quasar travels toward Earth, billions of light years for billions of years. On the way, it passes near a galaxy whose gravity bends space-time, and the light splits into two possible paths around that galaxy, one going left and one going right. Both eventually reach Earth. You have a detector that can be set up two ways. One detects which path the photon took. The other makes the two paths interfere with each other, which only works if the photon travelled both paths simultaneously as a wave. You make your choice about which detector to use after the photon has already passed the galaxy. The photon split, travelled for 1 billion years, and only now at the moment of detection do you decide whether it turns out to have been a particle that took one path or a wave that took both. And it works. If you choose the which path detector, the photon turns out to have taken a single definite path. If you choose the interference detector, the photon turns out to have taken both paths and produces an interference pattern. Your choice now appears to reach backward in time and determine what the photon was doing for 1 billion years before you made any decision at all. Experiments have confirmed this not with quasar light, but with laboratory photons and rapidly switched detectors. The choice of measurement determines the observable past behaviour of the particle. This isn't a theoretical puzzle sitting in a thought experiment. It happens in labs under controlled conditions. The conventional interpretation says there's no backward causation, because until measurement there was no fact of the matter about which path the photon took. The photon was in superposition. Your measurement creates the history, but there's no contradiction because there was no prior definite history to contradict. The past in this sense isn't fixed until it's been observed. That answer requires you to be comfortable with the idea that the past isn't real in the way we ordinarily assume. Events don't have definite properties before they're measured. Measurements don't reveal pre-existing properties so much as bring properties into existence. The photon's path for the last 1 billion years was genuinely undetermined until you set up your detector just now. Wheeler thought about this deeply and developed what he called the participatory universe, the idea that observers don't passively record reality, but actively participate in bringing it into being. Not just locally, but reaching back across cosmic timescales. He believed the universe required observers to have a definite past and didn't have one before observers evolved to look at it. That's either the most profound thing anyone has said about the nature of reality or a category error that sounds profound. Physicists haven't agreed on which. What nobody disagrees about is that the experiments show exactly what they show, and that the results are genuinely strange regardless of how you try to interpret them. Every photon that has ever travelled from a distant source to your eye made this kind of journey. Every observation you've ever made selected a history from a superposition of possible histories. The world you see is not a recording of events that happened independently of your looking at them. It's something stranger than that. Imagine looking at a star right now and understanding that your act of looking is participating in determining what that light was doing for thousands of years before you were born. In what sense is the past finished, and who finishes it? Wheeler proposed a cosmic version where quasar light travelling for billions of years serves as the photon source, and gravitational lensing serves as the beam splitter. Observing quasar light that travelled 2 billion years retroactively determines what the photon was doing when the universe was half its current age. Wheeler believed this was a direct consequence of quantum mechanics applied at cosmic scales. The quasar has been sending light for billions of years. Astronomers have been observing quasars for decades. Every observation has been retroactively determining the history of light that travelled before any human existed to observe anything. Many physicists prefer to say quantum mechanics doesn't require observers in the philosophical sense, just physical interactions that constitute measurements. The retroactive history determination doesn't require consciousness, just measurement. But the implication remains. There are events whose properties weren't determined until long after those events occurred in spacetime. The past is not as fixed as common experience suggests. Something about the act of measurement, even physical measurement with no conscious observer, retroactively selects from among possible histories. Much of what you take to be the fixed and finished past is, in some sense, being continuously established by the measurements happening now. Maxwell's demon. Imagine a tiny creature, small enough to see individual gas molecules, sitting at a frictionless door between two chambers of gas at the same temperature. The demon watches molecules approach, fast-moving ones heading right, it lets through. Slow-moving ones heading left, it lets through. Everything else it blocks. After a while, all the energetic hot molecules are on one side and all the sluggish cold molecules are on the other. A temperature difference exists where none did before. And you can run an engine on a temperature difference and extract useful work from it. James Clerk Maxwell proposed this in 1867 to probe what the second law of thermodynamics really means. The second law says entropy in a closed system never decreases. That's why heat flows from hot to cold, why things fall apart rather than spontaneously assembling, why broken eggs stay broken. But Maxwell noted the second law is statistical. Decreasing entropy isn't impossible in principle, it's just vanishingly unlikely. A demon tracking individual molecules could decrease entropy without violating any mechanical law. For decades, nobody could explain the flaw. The door is frictionless. The demon doesn't touch the molecules. Where's the energy cost that should save thermodynamics? Szilard pointed to measurement. The demon has to observe each molecule, which requires processing information. Landauer showed that erasing information has a thermodynamic cost. Each bit erased dissipates a minimum amount of energy as heat. The demon must continuously erase old measurements to keep measuring new ones. That erasure generates exactly as much entropy as the demon removes from the gas. The demon pays for everything it gains, but the resolution does something strange to physics. It connects thermodynamics to information in a fundamental way. Information isn't abstract. It has physical weight. Forgetting has thermodynamic consequences. Every time a physical system loses track of its own prior state, entropy increases. Memory and thermodynamics aren't separate domains. They're the same domain described in different vocabularies. What this implies is that the second law, the law that gives time its direction and distinguishes past from future, is ultimately about information, about what gets recorded and what gets erased. A universe where everything was perfectly remembered, where no information was ever lost, would be one where entropy didn't increase, where processes could run backward as easily as forward, where past and future would be much less distinct. The reason yesterday feels different from tomorrow isn't just about energy, it's about the accumulation of records of traces of the physical aftermath of events. History is physically encoded in the present state of the universe. When that encoding is lost, when information is erased, entropy rises. Maxwell's demon also points at an unresolved question in the foundations of quantum mechanics. Quantum measurement itself involves something like what the demon does, selecting a definite outcome from a superposition. Whether quantum measurement has a thermodynamic cost, whether the collapse of a wave function generates entropy in some fundamental way, is a question that sits at the unresolved intersection of quantum theory and thermodynamics. We can calculate the Landauer limit with extraordinary precision. We've verified it experimentally. What we haven't fully resolved is what it implies about the relationship between physical law and the structure of information, or why information should have physical weight in the first place. Imagine a universe where careful attention to the state of every molecule could, in principle, reverse local entropy decreases. The second law wouldn't be a fundamental law. It would be a statement about what happens when you're not keeping perfect track. What does it mean that the arrow of time is ultimately about what gets remembered and what gets forgotten? Quantum measurement itself has something like the demon's structure. A measuring apparatus selects a definite outcome from a superposition, processing information in the process. Whether quantum measurement has a thermodynamic cost is a question at the unresolved boundary between quantum theory and thermodynamics. Some physicists have argued that quantum decoherence the process by which superpositions lose coherence through environmental interaction, is fundamentally a thermodynamic process. The quantum world bleeds into classicality through constant information loss, analogous to the demon erasing its memory. If right, the quantum to classical transition might be thermodynamic at heart. Whether that's right or not, the demon permanently changed how physicists think about information. Before Szilard and Landauer, information seemed abstract and non-physical. After them, information is physical. It takes up space, it costs energy to erase, and it participates in the laws of thermodynamics. The demon revealed this connection by trying to subvert it. Every piece of information erased anywhere, a computer deleting a file, a brain forgetting a memory, any physical process losing track of its past, adds entropy to the universe. The demon is everywhere, paying the thermodynamic price for all the forgetting. What does it mean that the universe's tendency toward disorder is ultimately paid for by the act of not remembering? The EPR Paradox. Einstein didn't believe quantum mechanics was complete, and he wasn't confused about it. He understood quantum mechanics very well, and found what it implied deeply unacceptable. Along with Boris Podolsky and Nathan Rosen, he published a thought experiment in 1935 to show the theory must be missing something. Take two particles and entangle their quantum states, separate them across any distance, measure the spin of one and the quantum state of the other is instantly determined, even if no signal could have travelled between them. Einstein called this spooky action at a distance and thought it revealed something absurd. Either the two particles communicate instantaneously across any distance, violating relativity, or they had definite properties all along that quantum mechanics failed to describe. Hidden variables, pre-existing values that determine the measurement outcomes before any measurement was made. He believed the second option. Quantum mechanics, he argued, was an incomplete description of a deeper reality that already had definite answers before you looked. For nearly 30 years, this remained a philosophical dispute with no experimental resolution. Then John Bell published a theorem in 1964 showing the dispute was actually experimental. Hidden variable theories and standard quantum mechanics make different predictions for the statistical correlations between distant measurements. If hidden variables exist and are local, meaning they can't spread faster than light, certain correlations between distant measurements can't exceed certain mathematical bounds. Quantum mechanics predicts they can exceed those bounds. Experiments starting in the 1970s and refined repeatedly through the decades show the quantum mechanical correlations are real. Local hidden variable theories are ruled out. Einstein was wrong about this particular bet. The universe is, in some sense, genuinely non-local in the way quantum mechanics requires. But the resolution doesn't close the unsettlement, it just relocates it. What the experiments show is that the correlations are real and strong. What they cannot show is how those correlations are established. Measuring one particle seems to instantly fix the state of the other, but nothing physically travels between them. No signal passes. You can't use entanglement to send information faster than light because you can't control what result you get. Only observe it after the fact. The correlations are real. The mechanism is invisible. Physics has accepted entanglement as a fundamental feature of reality and learned to calculate with it precisely. The calculations work. What doesn't exist is a comfortable account of what's actually happening beneath the calculations. Different interpretations of quantum mechanics answer the EPR question differently and incompatibly. Copenhagen says asking what happens between measurements is meaningless, that there's no reality to the question. Many worlds says both measurement outcomes happen in different branches of a constantly splitting universe. Pilot wave theory says hidden variables exist, but they're non-local, connecting distant particles through the wave function itself. Each interpretation is mathematically equivalent to the others. Each makes the same experimental predictions. No experiment can distinguish between them. Entanglement has been demonstrated between particles separated by hundreds of kilometers. Quantum cryptography and quantum computing both exploit it practically. The phenomenon is real and useful. What it is remains contested. Somewhere two particles remember their shared origin, regardless of the distance between them. A measurement of one shapes the other, faster than light could ever travel. What is the connection made of when there's nothing in between? David Bohm developed pilot wave theory, where particles have definite positions at all times. guided by a real wave propagating through all space. Entangled particles share a wave function that connects them instantaneously across any distance. The theory makes identical predictions to standard quantum mechanics and has no internal contradictions. Most physicists don't like it because the non-local wave seems unphysical. But mechanism is exactly what EPR asks for and doesn't get in any interpretation. Entanglement correlations are instantaneous. Special relativity says nothing travels faster than light. These coexist through the argument that entanglement can't send information, so correlations don't violate relativity operationally. But the correlations themselves, as features of the world, rather than signals, seem to describe something instantaneously spread across space. Whether that's a deep fact about space-time or a sign that our concept of locality needs revision is a live question. Quantum gravity might change the picture entirely. The non-locality of entanglement and the non-locality general relativity requires in some formulations might be aspects of the same structure. Two particles, light years apart, share something. Measurement of one affects the other faster than any signal could travel. The universe permits this, and we can use it and calculate with it, and the question of what it means remains genuinely open. What kind of thing can be in two places at once and connect them with nothing visible in between? What kind of connection is made of nothing between them? Fermi's paradox. The math is straightforward enough to be alarming. Our galaxy contains somewhere between 100 and 400 billion stars. A significant fraction of those have planets. A significant fraction of those planets orbit in the habitable zone, where liquid water can exist. Life on Earth arose relatively quickly after conditions allowed it, suggesting it might not be extraordinarily difficult to get started. And the galaxy is 13 billion years old, which means civilizations with billions of years head start could, if they wanted to, have spread across the entire galaxy many times over, even travelling at a fraction of the speed of light. So where is everybody? That's Fermi's question, posed informally in 1950 over lunch. And in the decades since, it's become one of the most uncomfortable questions in science. Not because we lack possible answers, but because every answer we can construct requires something to be deeply wrong about our assumptions. And we can't tell which assumption to abandon. The absence is total. We've listened to the sky with radio telescopes for decades. We've scanned for laser pulses and unusual stellar spectra. We've searched for megastructures that advanced civilizations might build around stars. We've looked for anything that isn't adequately explained by known physics and found nothing. Not a signal, not an artifact, not a probe, not even an anomaly we can't explain. Some answers to Fermi's question involve making life rare. Maybe the origin of life really is extraordinarily unlikely. A sequence of events so improbable that we might be the only planet it happened on in the observable universe. Maybe complex animal life requires conditions so specific that almost no planet ever hosts it. Maybe intelligence requires conditions even more specific. Every bottleneck you add to the chain from simple chemistry to technological civilization reduces the expected number of communicating civilizations. And if enough bottlenecks exist, the number could be less than one per galaxy. Other answers involve civilizations destroying themselves, nuclear weapons, engineered pathogens, artificial intelligence that optimizes for goals incompatible with biological life, climate change. Any number of technologies might reliably wipe out civilizations before they reach interstellar capability. If something reliably kills civilizations, the universe could be full of microbial life and empty of anything that broadcasts radio signals. There's a darker version of this. If some technology consistently destroys civilizations, and if that technology is somewhere on the path that every civilization takes, then we should expect to hit that technology at some point. The silence of the universe is, on this reading, a warning. Something kills civilizations before they become audible to their neighbours. We haven't been audible for long. The most disturbing answers involve civilizations that exist but choose silence or invisibility. Maybe broadcasting is dangerous. Maybe something is out there that treats signals as targets. The dark forest hypothesis, which science fiction writer Liu Cixin developed into a narrative, but which has a serious version in game theory, proposes that civilizations that reveal themselves to the universe risk being destroyed by others who can't afford to take chances on unknown neighbours. Silence is strategy. We've been broadcasting for about a century. Radio waves from Earth have reached roughly 100 light-year radius of space. What's in that sphere is unknown. What might be listening is unknown. If the silence ends, what kind of answer would you hope for? There's a version of the problem that's become known as the Great Filter. If we're alone or nearly alone in the galaxy, something must be filtering out life or intelligence at some stage. Either the filter is behind us, in our past, meaning we already got past the hard step, or it's ahead of us, meaning we haven't hit the thing that kills civilizations yet. If the filter is behind us, we might be genuinely rare and special, one of the first complex civilizations in a galaxy that will eventually be filled with them. That's good news. If the filter is ahead, it's extraordinarily bad news. It means something on our trajectory reliably ends civilizations. Something we're approaching or something we're building. The silence of the universe would be the sound of civilizations ending before they became audible. Finding microbial life on Mars or evidence of past life would be disturbing rather than exciting under this framework. It would mean the filter is not at the origin of life, not at single-celled organisms, not at the early steps we already know about. It would mean the filter is somewhere ahead of us, and whatever killed those Martian organisms might be the same thing that waits for us. The absence of detected alien civilizations is consistent with us being alone. It's also consistent with civilizations being common and something killing them before they broadcast. It's also consistent with civilizations choosing not to broadcast. What it's not consistent with is the naive assumption that the universe is full of beings who are detectable and benign and simply haven't made contact yet. 100 billion stars, billions of years, and nothing we've found so far that we can't explain without invoking other minds. What would it actually mean if we found out we were the first? The Blob Paradox. Physarum polycephalum is a slime mold. Not a mold exactly, and not a fungus, and not quite an animal or a plant. It's a single-celled organism that can grow to the size of a dinner plate, navigate mazes, solve optimization problems, and respond adaptively to its environment, all without a brain, without neurons, without anything that resembles what we usually mean when we say the word mind. When you cut it in half, both halves survive and grow into independent organisms. When two pieces of it encounter each other, they can fuse back into a single organism, carrying whatever each piece learned during their separation. Whether the two separated pieces and the reunited thing they become are one organism or two or three is a question that doesn't have a clean answer. The Blob Paradox asks what the concept of an individual means in biology, and the answer turns out to be much less clear than we assume when we apply the concept to creatures like ourselves. Consider what makes you one organism rather than many. You have about 37 trillion cells. Each of them carries the same genetic information and coordinates its activity with the others through chemical and electrical signals. You have one coherent sensory experience, one continuous stream of consciousness, one will that issues instructions to your limbs. The individuality feels obvious and unambiguous. But the human body contains roughly the same number of bacterial cells as human cells. The microbiome isn't just present in your gut. It communicates with your immune system, influences your brain chemistry, affects your mood and behavior in ways still being documented. At what point do you and your microbiome stop being a host and its inhabitants and become something more like a composite organism? The line is not clear, and it may not be real in any deep biological sense. Now go further. Aspen forests can consist of thousands of trees that share a single root system. All the trees in a given grove might be genetically identical, connected underground, sharing resources and possibly information through fungal networks. The trees look separate. They're distinct objects in space. But whether they're thousands of individuals or one organism spread across hillsides is a question that biology hasn't settled, and may not be able to settle without first deciding what question it's really asking. The blob makes this vivid because it can physically separate and reunite. Two blobs that developed independently for weeks can merge and immediately begin functioning as a single integrated system. The merged blob shows evidence of integrating information from both predecessors. If the blob that was cut in half and then rejoined is the same blob, what does same mean here? If it's a different blob, what changed? What the blob reveals is that individuality in biology might be less a natural kind than a useful fiction. We apply more or less successfully to different cases. Organisms at the cellular level are constantly exchanging components with their environments. Boundaries between self and world are maintained by active biological processes rather than by any sharp ontological distinction. The blob just makes those boundaries optionally maintained rather than robustly stable. There's a version of this that applies to the concept of species as well. Species boundaries blur in evolutionary time, merge and split, sometimes coexist with hybridization. What looks like a clean category, when examined on a human timescale, dissolves when examined across millions of years. Physarum polycephalum solved the Tokyo subway routing problem when researchers placed food at points corresponding to major population centers. Without any plan or any planner, it grew its network in a pattern that approximated the actual subway system, minimizing energy use across the network. Whatever it's doing when it does this, it's doing it without a brain, without neurons, without anything we'd recognize as cognition. What kind of thing processes information, solves problems, and learns without having anything we'd call a mind? The individuality problem connects to deeper questions in philosophy of biology about what a natural kind is. We tend to assume that biology carves nature at its joints, that species and organisms are real things in the world rather than convenient groupings we impose. The blob complicates that. An organism that can split and reunite, that might be one thing or many things depending on how you count, doesn't fit cleanly into the categories we use to describe the living world. Slime molds can switch between unicellular and multicellular modes depending on resource availability. During the multicellular phase, some cells sacrifice themselves for the collective, showing all the hallmarks of individual organism behavior. Which mode is the real one? The question might not be pointing at a real distinction. The blob is actually being studied now for its potential in computing. Its ability to optimize networks without centralized control, to adapt to changing conditions, and to apparently retain information about past states without neurons has attracted serious scientific attention. Engineers want to understand the mechanism, which means first understanding what it is that does the computation. What computes, when what computes has no part that resembles what we think computation requires? Schrödinger's cat. Erwin Schrödinger devised his cat as a criticism, not a celebration. He wanted to show that quantum mechanics, as it was being interpreted, led to conclusions so absurd that the interpretation had to be wrong. Instead, he created an image so striking that it's become the most recognizable symbol in all of quantum physics, appearing on t-shirts and magazine covers and pop science explainers. The cat ate its creator. The setup works like this. A cat is sealed in a box along with a tiny amount of radioactive material, a Geiger counter, a vial of poison, and a mechanism that breaks the vial when the Geiger counter detects radioactive decay. After 1 hour, the probability of radioactive decay is exactly 50%. Inside the box, the atom either decayed or it didn't. The cat is either dead or alive. Quantum mechanics says that before measurement, a quantum system in superposition doesn't have definite properties. The atom isn't in the decayed or not decayed state, it's in a superposition of both. The Geiger counter is entangled with the atom. The mechanism is entangled with the Geiger counter. The vial is entangled with the mechanism. The cat is entangled with the vial. Before you open the box, according to the Copenhagen interpretation, the cat is in a superposition of alive and dead states. Schrödinger thought this was obviously wrong. Cats don't exist in superpositions. Things that size don't behave quantum mechanically in any observable way. Something collapses the superposition before it gets to the cat. But quantum mechanics doesn't specify what that something is. The equations don't draw a line between the quantum and classical worlds. They don't identify a scale at which superpositions stop applying. 80 years later, they still don't. The measurement problem, the question of why observation produces definite outcomes from superpositions, is unresolved. Different interpretations of quantum mechanics handle it in incompatible ways. Copenhagen says measurement collapses the wave function, but doesn't explain what counts as a measurement or why collapse happens. Many World says the cat is alive in one branch of the universe and dead in another, and the observer splits into two versions. Decoherence explains why we don't observe superpositions at macroscopic scales, but doesn't fully explain why measurement gives a single definite outcome. Experiments have pushed quantum superpositions to increasingly large scales. Molecules of 60 or more atoms have been shown to exist in superposition. Microscopic vibrating objects have been cooled to their quantum ground state. The line between quantum and classical has been pushed further than Schrödinger imagined, but it hasn't disappeared. What makes the cat problem more than a philosophical puzzle is that it connects to every interpretation of quantum mechanics, and therefore to every attempt to understand what quantum mechanics is actually saying about reality. Whether the wave function is real, whether there's a physical collapse, whether the universe splits at every quantum event, whether consciousness plays any role in measurement, all of these questions have the cat sitting somewhere in the middle of them. Somewhere in a thought experiment that's been running since 1935, a cat waits for an answer that physics hasn't given yet. What kind of thing can be genuinely both states at once, and what decides which one it becomes? If measurement collapses superpositions, and if a measuring apparatus is itself quantum mechanical, then the apparatus should also exist in superposition until something measures it. And whatever measures the apparatus should exist in superposition too. The chain has no natural end unless you insert something outside the quantum system, something that collapses without needing to be measured. Some early physicists suggested consciousness was that something. Consciousness collapses the wave function. This interpretation has been mostly abandoned because it creates its own problems, including how much consciousness is needed, and whether a mouse looking at the apparatus collapses things differently than a human. The many worlds interpretation avoids the collapse entirely. The cat is alive and dead. The universe splits into two versions, one in which the cat is alive and you observe it alive, one in which the cat is dead and you observe it dead. You experience only one branch because you are inside it, but the other branch is equally real and contains a version of you who saw the other outcome. Every quantum event that could go differently does go differently, somewhere in some branch of the universal wave function. This is either the most extravagant ontology in the history of physics, or a natural consequence of taking the mathematics seriously without a collapsed postulate. Adherents say the theory contains no exceptions and no arbitrary additions. Opponents say it requires uncountably many unobservable universes, which is a high price. No interpretation has made the strangeness go away. Quantum mechanics works better than any other theory in history. Every calculation agrees with experiment. What it's describing is genuinely unclear, and the cat sits inside that unclarity, waiting for physics to resolve something it hasn't found a way to resolve. What would it mean to know the answer? And would the answer feel like finding something familiar or something unrecognizable? The twin paradox. Two identical twins. One stays on Earth, the other boards a spacecraft and accelerates to a significant fraction of the speed of light, travels to The twin paradox. Two identical twins. One stays on Earth, the other boards a spacecraft and accelerates to a significant fraction of the speed of light, travels to a distant star, decelerates, turns around, accelerates again, and returns. When they meet, the travelling twin is younger. Not metaphorically younger. Physically younger, with less biological wear, fewer heartbeats accumulated, a measurably shorter life elapsed. If the trip took 30 years by Earth clocks, the travelling twin might have experienced only a handful of years. Special relativity predicts this, and experiments confirm it. Atomic clocks on jets flown around the world return slightly desynchronized from identical clocks left on the ground. GPS satellites have to correct for time dilation constantly, or the navigation system would accumulate errors of kilometers per day. Time dilation is not a theoretical curiosity, it's an engineering consideration. But here's what seems paradoxical. Relativity says motion is relative. From the travelling twin's perspective, it's the Earth twin who moved away and returned. So shouldn't the Earth twin be younger by the same logic applied symmetrically? The resolution involves something that's easy to state but genuinely strange to think about. The travelling twin's journey is not symmetric with the Earth twins. The traveller accelerates, decelerates, turns around, and accelerates again. Acceleration is absolute, not relative, in special relativity. You can feel it. The traveller can measure the g-forces. The Earth twin sits in an inertial frame throughout. Their experiences are physically different, not just observationally different, and the asymmetry explains why the aging is asymmetric. So time passes more slowly for the accelerating twin. That's the resolution to the apparent paradox. But the resolution just relocates the strangeness. What time dilation means is that time is not a single universal backdrop against which events unfold. Time passes at different rates depending on your state of motion and your gravitational environment. There is no absolute now, no universal present moment that all observers share. Your now and my now are only approximately the same because we're moving at approximately the same velocities and sitting in approximately the same gravitational field. Push this further. Two events that are simultaneous in one reference frame are not simultaneous in another. Whether two things happen at the same time is not an objective fact about the universe. It's a fact relative to a choice of reference frame. The ordering of some events in time can actually be reversed depending on how fast you're moving relative to them. Most of what we assume about time, that it flows uniformly, that there's a universal present, that the sequence of events is fixed, is an approximation that works well at low speeds and weak gravitational fields. At the edge of the approximation, time becomes personal. What does it mean for two people to share a moment when each of them is living in their own version of time? If there's no universal now, the concept of the universe at a given instant doesn't have a clear meaning. Different observers moving at different velocities slice space-time into different sets of simultaneous moments. What's happening right now on the other side of the galaxy depends on how fast you're moving relative to that galaxy. This is not a failure of knowledge. It's not that we just can't measure what's happening simultaneously. There is no simultaneous happening that's observer independent. The universe doesn't have a single present tense. It has a history, a four-dimensional block of space-time in which events are arranged in a way that's partly fixed, the light cone structure that determines what can influence what, and partly flexible, the precise simultaneity of distant events. The implications for causation are strange. Cause must precede effect, but precede by whose clock? Events that are in the causal future of an event for one observer must be in the causal future for all observers because the light cone structure is preserved. But events that are simultaneous for one observer are in the future for another, and in the past for a third. Simultaneity is not just relative, it's physically meaningless for space-like separated events. And yet we experience time as flowing. We experience a present moment. We experience duration, the felt sense of being in time, of moving through it, of now being different from then, is one of the most immediate features of consciousness. Special relativity says that feeling is, at minimum, highly perspective dependent, relative to the observer's inertial frame. The travelling twin returns younger. That's a real, measurable fact. Two people can share the same space-time location and have different amounts of past. The older twin has had more heartbeats, more thoughts, more biological wear. The younger twin was in a different region of space-time and experienced less of its passage. Somewhere in the universe, clocks are running at different rates depending on how they're moving and what they're near gravitationally. Every clock you've ever looked at, including the one in your chest, has been running at a rate slightly different from every other clock. What does it mean to be alive for a certain amount of time when time is a thing you can travel through at different speeds? Olbers Paradox. Look at the night sky. Between any two stars you can imagine aiming at another star further away. Between any two dark patches, you can imagine that there's a star beyond them, just too faint to see. If the universe is infinite and contains stars distributed throughout in all directions without end, then every line of sight you cast into the sky should eventually terminate on the surface of a star. The sky should glow as brightly as the surface of a sun, uniformly, in every direction, day and night. The sky is dark, that's the paradox. Heinrich Wilhelm Olbers restated this problem clearly in 1823, though it had been noticed earlier. Edgar Allan Poe, of all people, published a correct solution in 1848 in a prose poem called Eureka, before professional astronomers arrived at the same conclusion. The sky is dark, Poe proposed, because the universe has a finite age. Light from sufficiently distant stars hasn't had time to reach us yet. We're seeing only the portion of the universe that's had time to send us its light. The universe is about 13.8 billion years old. Light travels at a finite speed. We can only receive light from objects within roughly 46 billion light years, the observable universe. Beyond that, light from stars simply hasn't reached us yet. Dark not because there's nothing there, but because there hasn't been enough time. The expansion of the universe adds another effect. Light from distant galaxies is redshifted as space expands, stretching the wavelength from visible light toward infrared and microwave frequencies invisible to the naked eye. The universe is actually filled with light from the early universe, what we call the cosmic microwave background radiation, but it's been stretched to a wavelength we can't see without instruments. So the darkness of the night sky encodes two fundamental facts about the universe. It has a finite age and it's been expanding since its beginning. The darkness is not emptiness. It's the horizon of what time has had the chance to make visible. But think about what lies beyond that horizon. There's every reason to believe the universe continues past the point where light has had time to reach us. Other galaxies, other stars, other possible observers, all of them beyond what we can ever see. Not because space ends, but because time began. If the universe is infinite, there are infinite stars that will never be visible from here, no matter how long we wait, because the expansion of space is carrying them away faster than light can cross the growing gap. The night sky is a window into a finite slice of something that may be infinite. What you're seeing when you look up is the boundary of knowability drawn by the age of time. What might be out there in the dark that no amount of waiting will ever make visible? The observable universe contains on the order of 2 trillion galaxies, each with hundreds of billions of stars, numbers large enough to stop being meaningful. And yet all of that radiated energy produces a night sky that's dark. Part of the resolution is timing. Light travels at a finite speed. Looking out at the universe is looking back in time, because the light you're seeing left its source in the past. The furthest objects we can see emitted their light billions of years ago. The universe back then was different, younger, in some regions denser. The light we receive encodes that past state, not the present state of those regions. Another part is the expansion. Not only is light finite in speed, but the space it travels through is expanding. Distant galaxies are receding from us, and beyond a certain distance they're receding faster than light. Not because they are moving through space faster than light, but because space itself is growing. Light from those galaxies, already travelling toward us, is losing the race. It will never arrive. Those galaxies are permanently beyond our horizon. What makes Olbers Paradox resonate past its resolution is the image it produces. We live inside a sphere of visible universe. Outside that sphere, in every direction, there are things we can never see. Not because of any failure of our instruments, but because of the geometry of space-time and the finiteness of time. The darkness isn't empty, it's full of light that hasn't arrived yet, from stars that may or may not still exist, from galaxies whose current state is unknowable. The universe is almost certainly larger than the part we can see. Whether it's finite or infinite is unknown. If it's infinite, the part we're in is an infinitesimal sample, and questions about whether the whole has the same properties as our sample have no good answer. You look up at the dark and you're looking at the edge of what's knowable. Not the edge of existence, just the edge of what time has allowed to reach you. What's on the other side of the darkness? And in what sense does the question have an answer? What you're seeing when you look at the dark is the boundary of knowability drawn by the age of time. Not empty space, not nothing. The edge of what light has had time to cross. Every photon reaching your eye tonight left its source at some point in the past. Some of those sources no longer exist. You're seeing the light of dead stars. The sky is full of messages from things that might be gone. What does it mean to see light from something that might no longer exist? And in what sense is that thing still there? The Grandfather Paradox. Imagine a time machine. Not the philosophical kind that asks about identity or memory, just a mechanical device that moves you backward in time. You get in, set the dial, and arrive in the past. You find your grandfather as a young man, before he met your grandmother, before your parent was born. You have the means, and for some reason the motivation to kill him. You do. Now you cannot be born. But if you were never born, you never built or used the time machine. You never travelled back. You never killed your grandfather. So he lived, your parent was born, you were born, you built the time machine, you travelled back. You killed him. Around and around. Every direction leads to a contradiction. This is the Grandfather Paradox. And it seems to show that backward time travel is logically impossible, rather than just physically unlikely. Not hard to do. Conceptually incoherent. If you could go back and change the past, you could create a situation with no consistent state, and physical reality presumably can't be in an inconsistent state. The standard physicist's response has been to invoke self-consistency. Only histories that don't produce contradictions are physically possible. You might be able to travel to the past, but something would always prevent you from actually killing your grandfather. The gun would jam, you'd miss, something would intervene. The universe would conspire to preserve consistency. This is actually less hand-wavy than it sounds. The Novikov self-consistency principle, developed by physicist Igor Novikov, proposes precisely this. In spacetimes that allow closed time-like curves, the only histories that occur are self-consistent ones. The constraints aren't imposed by a supernatural force, but by the mathematics of what solutions to the equations of general relativity actually exist. But the grandfather paradox reveals something deeper than just a puzzle about time travel. It asks what we mean by causation. In ordinary physics, the past causes the future. Causes precede effects. Events have a direction. The grandfather paradox puts you in a situation where the future appears to cause the past, and then the past causes the future in a closed loop with no beginning. Where does the loop start? What's the first cause? Closed causal loops have no first cause. Everything in the loop is caused by something else in the loop. The time traveler kills the grandfather because the grandfather lives and the time traveler is born. And the grandfather lives because the time traveler is born and kills him at a time that doesn't prevent the birth, and so on. The loop is self-causing. Whether the universe permits self-causing loops is a question about the deep structure of space-time, and it's connected to whether black holes and certain solutions to Einstein's equations that seem to allow time travel are physically realizable, or some mathematical artifacts. General relativity permits them. Whether quantum mechanics does is unresolved. Somewhere in the logic of causation, something is either impossible or stranger than it seems. If you could go back and change the past, would you be changing anything, or just revealing what the past already contained? The grandfather paradox connects to a broader problem about the structure of time. Physics laws are time symmetric. The equations of mechanics, electromagnetism, and quantum mechanics work the same forward or backward. You can run a film of billiard balls backward, and the reversed version still satisfies the laws of physics. Time's direction is imposed by initial conditions and statistical entropy, not by fundamental law. If time travel were possible, you could potentially use it to set up situations where information or causation flows backward through time. You could receive a message from your future self before you send it. You could know the outcome of events before they occur. The entire structure of how we think about knowledge, prediction, and possibility would need to be revised. General relativity, which governs the large-scale structure of space-time, does allow solutions in which closed time-like curves exist. These are paths through space-time that loop back to their starting point in time. A particle or a person following such a path would return to their own past. The mathematics doesn't forbid it. Whether it's physically realizable in any achievable scenario is a different question. Kurt Gödel, the logician, found exact solutions to Einstein's equations in 1949 that contain closed time-like curves in a rotating universe. Gödel was reportedly disturbed by his own result. If the equations allow time travel, and the equations are supposed to describe physical reality, then time travel is either physically possible, or the equations are more general than physical reality in some important way. Hawking's chronology protection conjecture says quantum effects build up at the boundary of would-be time machines and destroy them. But it's a conjecture. We don't have the theory of quantum gravity to prove or disprove it. The grandfather paradox might be impossible because nature prevents it. Or it might be impossible because it's logically incoherent. Or it might be not quite impossible but constrained to self-consistent loops that look different from what the word paradox suggests. What's the real reason the past can't be changed if it can't? The Newcomb Paradox. There's an entity that predicts human choices with near-perfect accuracy. Not theoretical near-perfect, nearly but not quite perfect, in a way that's been verified across millions of trials. Call it the predictor. It presents you with two boxes. Box A is transparent and contains $1,000. Box B is opaque. If the predictor predicted you would take only box B, it put $1 million inside. If it predicted you would take both boxes, box B is empty. The prediction was made yesterday. The contents of both boxes are already fixed. You can't change what the predictor put inside. You're standing in front of the boxes right now, and you have to decide. Do you take both boxes, or only box B? Two arguments pull in opposite directions with equal apparent force. The first says, take only box B. The predictor's accuracy is established. People who take only box B nearly always leave with $1 million. People who take both nearly always leave with 1,000. If you want $1 million, take box B. The second says take both boxes. Whatever the predictor predicted, it already made its choice. The contents of box B are fixed. If box B contains $1 million, taking both gives you $1 million and 1,000. If box B is empty, taking both gives you 1,000 rather than nothing. In either case, taking both boxes gives you 1,000 more than taking only box B. Always take both. Both arguments are valid under different decision theories. One boxing follows what's called evidential decision theory, which says choose the action that is most strongly evidenced to correlate with good outcomes. Two boxing follows causal decision theory, which says choose the action that causes the best outcome through the direct causal chain. The paradox has no consensus resolution. Surveys of professional philosophers find roughly equal division. Papers defending each position appear regularly in academic journals. Both positions have serious, careful defenders who understand both arguments. What makes this more than a puzzle about fictional scenarios is that it points to a real and unresolved question in decision theory about the relationship between correlation and causation in rational choice. When you are the kind of person who makes a certain kind of choice, you may be correlated with certain outcomes through paths that don't involve your choice directly, causing those outcomes. Should you factor that into your decision? If you're wondering whether the predictor is physically possible, that's a separate question, but one with real-world relevance. Suppose instead that a scan of your brain this morning predicted your choice with 90% accuracy. Or that your past behaviour statistics predict with 85% accuracy that you'll 2-box. At what level of predictive accuracy does the 1-boxer's argument start to feel compelling? And somewhere underneath the decision theory, there's a question about free will. If the predictor can predict your choice, in what sense is your choice free? And if your choice is free in the relevant sense, how can anyone predict it with near certainty? What would you do? And what does your answer reveal about what kind of rationality you trust? If you're the kind of being whose choices can be predicted with near perfect accuracy, your choices are determined by something. If they're determined, in what sense are they free? And if they're not free, why does it feel like you're genuinely deliberating? Like the outcome is open? 1-boxers say the 2-boxing argument relies on a confused picture of agency. You're not a detached observer. You're part of the causal structure. The kind of deliberator you are is entangled with what the predictor placed in the box. Your choice and the prediction share causes. 2-boxers say this conflates structure with causation. At the moment of decision, the boxes are fixed. Correlation between your choice and the box contents doesn't mean your choice causes them to be different. Taking both boxes gets you 1,000 more, regardless of what's inside box B. Neither side has managed to convince the other in decades of argument. The problem illuminates something genuine and unresolved at the intersection of decision theory and causation. Every decision you make is arguably a Newcomb problem in miniature. Other people model you. Your reputation is based on their predictions. You're always confirming yourself to be a certain kind of predictor, and that has consequences that precede the individual choices. What kind of rational agent are you, and does knowing that change what you choose? What kind of rational agent are you, and does knowing that change what you choose? There's one more layer. The Newcomb problem assumes near-perfect prediction, but even imperfect prediction, if it's better than chance, changes the expected value calculation in ways that favour 1-boxing for sufficiently accurate predictors. The question of where the threshold sits, where prediction becomes accurate enough that 1-boxing becomes rational, even for causal decision theorists, is itself unresolved. What's certain is that the two arguments don't dissolve when examined carefully. Both are valid under reasonable assumptions, and the reasonable assumptions can't both be right at once. What does it reveal about rationality that two clear, careful arguments with obvious conclusions can point in opposite directions? The Bootstrap Paradox. A man travels back in time and gives young Beethoven the sheet music for the Fifth Symphony. Beethoven, who had composed nothing yet, copies it out and publishes it under his name. Centuries later, that same man, fascinated by the symphony, travels back in time and gives it to young Beethoven. Who wrote it? The answer is nobody. The symphony exists in a closed causal loop with no origin point. It was never composed. Every version of it is a copy of a copy with no original. The information has been circulating through time uncreated for centuries. That's the Bootstrap Paradox, sometimes called the ontological paradox, and it's distinct from the grandfather paradox because there's no contradiction. The loop is self-consistent. The symphony exists at every point in the loop. Nobody's grandfather gets killed. The timeline doesn't collapse. From the outside, and if you could see the whole loop at once, everything would look fine. The symphony is always there when you look. From the inside, it's a different kind of unsettling. Causation usually has a direction. Effects follow causes. Energy and information have to come from somewhere. The Bootstrap Paradox creates an object or a piece of information that appears to have come from nowhere, that exists without ever having been created, sustained purely by the logic of its own loop. Physical law generally conserves things. Energy can't be created or destroyed. Information, according to quantum mechanics, can't be destroyed either. Whether information can exist without ever having been created is a question the Bootstrap Paradox puts directly on the table. If the loop is self-consistent and violates no conservation law at any point within it, does that mean it's physically possible? Or does the absence of an origin point constitute a kind of violation that physics should prohibit? General relativity allows solutions to its equations that contain closed time-like curves, the mathematical structures that would make bootstrap loops possible. The Novikov self-consistency principle, designed to prevent grandfather-style paradoxes, actually supports bootstrap paradoxes. Consistent loops without contradictions are the very solutions Novikov's principle selects for. So physics seems to permit the bootstrap paradox, at least at the level of general relativity. Whether quantum mechanics does is less clear, and whether a physical universe could actually contain information that has no causal origin, that bootstrapped itself into existence through a loop, is a question that touches the foundations of what causation even means. There's a version of this that doesn't require time machines. Imagine you learn a proof for a mathematical theorem from a book. You publish the proof. The original author of the book learned it from your publication. The proof circulates in academic literature, with no one able to identify who first worked it out, because no one did. The bootstrap loop exists in ordinary time, just spread across decades rather than running through a machine. Ideas do this. Cultural forms do this. Where did the first joke come from? Where did the first metaphor come from? Tracing the causal origin of certain kinds of information leads to regressions that don't resolve. The Bootstrap Paradox makes this explicit and impossible to dismiss. An object or a piece of information that has always existed within a loop and was never created sits at the edge of what causation can describe. If something has existed forever within its own loop, did it ever come from anywhere? There's a version of this that philosophers call the information ontology problem. In ordinary physics, information is conserved, but it always has an origin. Every configuration of matter traces back causally to a prior configuration. Even the Big Bang, if it had a cause, would be that cause. But what's the cause of information in a bootstrap loop? The loop is self-sustaining, causally closed, internally consistent. But it appears to violate the intuition that everything has an origin. Some physicists take bootstrap loops seriously as possible features of a universe that permits closed time-like curves. If the laws of physics allow for self-consistent loops without origins, then the ontological intuition that everything must come from somewhere might just be wrong. Or it might be true in our universe precisely because our universe doesn't permit the loops, which would make the absence of bootstrap paradoxes in ordinary life a consequence of the structure of time rather than a logical necessity. On some views of physics, the past exists as a fixed part of a four-dimensional block universe. The bootstrap loop isn't an object without an origin, so much as a region of spacetime with a particular structure. Asking what created the symphony becomes as odd as asking what created the shape of a mountain. The symphony exists in the loop because it always has. Always here means at every point in the loop's timeline rather than in any time before the loop. There is no before the loop simply is. And the music in it is simply there, uncreated, circulating through its own past and future with no point of entry. What kind of existence is that? And is it different in any meaningful way from the existence of anything else? What kind of existence is that? And is it meaningfully different from ordinary existence? The Teleportation Paradox. Imagine a machine that works like this. You step inside, every atom in your body is scanned and recorded with perfect precision. Your body is then disassembled. The information is transmitted instantaneously to a receiver on Mars. At the receiver, a new body is assembled from locally available atoms, configured exactly as the scan specified. The machine destroys the original and builds the copy. You arrive on Mars in seconds. Now ask the question everyone asks. Is it you? The person who steps out on Mars has all your memories, all your habits, all your mannerisms, your face, your fingerprints, your emotional patterns. They wake up believing they just teleported. From their subjective perspective, the experience was continuous. They remember stepping into the machine. They feel like they arrived. But you, the person who stepped into the machine on Earth, were disassembled. The specific arrangement of atoms that was you stopped existing. A new arrangement with an identical configuration was assembled elsewhere. Whether continuity of experience bridges that gap, or whether something was lost in the gap, is a question that depends on what you think you are. If you're a pattern, a specific arrangement of matter that carries information, then teleportation preserved the pattern, and you arrived on Mars. The substrate changed, but the pattern is intact. You're like a song that can be played on different instruments. What matters is the music, not the specific strings or pipes producing it. If you're a continuous physical object, a particular collection of particles with an unbroken causal history, then you didn't survive teleportation. The original person died in the disassembly. A copy, perfect in every detail, stepped out on Mars believing itself to be you. The copy is not lying and is not confused. It has every reason to believe it survived. But the original is gone. Derek Parfit spent much of his career on exactly this problem. He concluded that personal identity might not matter in the way we assume, that what we care about is psychological continuity and connectedness, and those can be preserved through teleportation. Whether Parfit is right depends on whether psychological continuity is doing all the work. Most people initially insist they couldn't survive teleportation. Then they're asked whether they survive dreamless sleep. The criteria turn out to be less stable than they appear. Now add a complication. The machine malfunctions and both copies survive. They step forward equally convinced of their identity, equally continuous with the original. There's no fact of the matter distinguishing them. Personal identity may not be a relation that survives branching in any coherent way. If two people wake up tomorrow each believing they're you, and each has an equal claim to being you, what does that mean you were yesterday? Suppose the teleporter builds the copy first, runs it for a moment, and only then destroys the original. For that moment, two versions of you exist, then one is terminated. The remaining one is, from its own perspective, continuous with the original. Which one was terminated? You'd probably say the original on Earth. And the Mars copy survived. But the Mars copy has an identical claim to being the original. It has the same memories, the same felt sense of continuous experience, the same identity, documents. The answer to which was terminated is not determined by any fact about either body. It's determined by the arbitrary sequencing of the procedure. Imagine a malfunction, and both copies survive. They diverge immediately, make different choices, develop different memories. After a year, neither has a stronger claim to being you than the other. Parfit found this liberating rather than terrifying. If personal identity is not what matters, then what matters is the psychological continuity and connectedness that both copies share. Both are, in the relevant sense, you. Not numerically identical to you, but connected to you in the ways that matter. Death on the teleporter's stage isn't death in the sense that matters if something psychologically continuous emerged at the other end. Most people don't find this liberating, the sense that there's something irreducibly individual about personal identity, something that can't branch or split or be satisfied by having a copy, is strong and persistent, even in the face of philosophical argument. Whether that sense tracks something real or is an artifact of how consciousness presents itself from the inside is one of the questions the paradox was designed to make unavoidable. What is the thing that couldn't possibly be you, even if it were identical to you in every measurable way? Parfit found this liberating. Both copies share psychological continuity, which is what matters. Most people don't find it liberating. The irreducible individuality of personal identity feels real even against the argument. What is the thing that couldn't possibly be you even if it were identical to you in every measurable way? Your body replaces most of its atoms over years, You've already survived a slow-motion version of teleportation many times over. Whether the rapid version preserves what ordinary existence already preserves is the question. What is the thing that couldn't possibly be you, even if it were identical to you in every measurable way? The Ship of Theseus. Theseus returned from Crete on a ship the Athenians preserved as a memorial. Over centuries, the planks rotted and were replaced one by one, then the ropes, the sails, the fittings, until, as Plutarch noted, not a single original piece remained. The Athenians still called it the Ship of Theseus. Was it? At any given moment during the long process of replacement, the ship seemed continuous with its past. Replace one plank, and you still clearly have the same ship. Replace a second, and nothing has changed about that verdict. Keep going, and at some point you have a ship made entirely of new materials, with no physical connection to the original vessel. The paradox asks where the ship stopped being itself, and the uncomfortable answer is that there's no principled place to draw that line. Now imagine a second version. A collector has been gathering all the original planks as they were replaced, restoring them, and has now assembled a complete ship using only the original materials. Which ship is the Ship of Theseus? The continuously maintained one that's been in the harbour all along, or the reconstructed one made of the original materials? You probably have an intuition, but it may not survive contact with the next variation. Suppose the planks were replaced so slowly that one per decade was swapped out. Suppose they were replaced all at once in a single dry dock session. Does the speed of replacement matter? Most people say no. And then the question is, what does matter? And the list of candidates keeps producing counterexamples. The Ship of Theseus problem isn't just about boats. Heraclitus put the core insight in a river. You can't step into the same river twice because new waters are always flowing. The river is constituted by process, not by a fixed collection of stuff. Whether that's true of other things depends on what kind of thing they are. Your body replaces most of its atoms over 7 to 10 years depending on the tissue. The neurons in your cortex are mostly with you for life, but their connections, the synaptic structure that stores your memories and shapes your personality, is constantly being pruned and grown. The you of 10 years ago shares continuous physical history with the you of now, but the stuff is different, and many of the configurations are different. Does that make you a ship that's been gradually replaced? If so, in what sense is tomorrow you the same person as today you? Psychological continuity theories say what matters is the chain of memories, not the substrate. But psychological continuity comes in degrees. The you of 30 years from now may share almost nothing with the you of today. At what point does the thread become too thin? Four-dimensionalist philosophers have a technically clean answer. Objects persist through time by having temporal parts, stages, or slices that are connected in the right ways. The ship at any moment is a temporal stage of a four-dimensional entity that extends through time. Whether two temporal stages are stages of the same ship depends on whether they're connected by the right continuity relations. But this just relocates the problem to specifying the right continuity relations, which turns out to be as difficult as the original question. What holds the ship together across time? And is it the same thing that holds you together? If the ship is a four-dimensional entity extended through time, what makes the temporal stages of the replaced ship connected to the original rather than the stages of the reconstructed ship? Both have equal physical continuity with the original. You might say the continuously maintained ship is connected by an unbroken chain of spatial continuity across time. The ship was always in the harbour, always the object called the Ship of Theseus. That spatial and social continuity is what makes it the ship. But spatial continuity is also compatible with total material replacement, and social continuity sounds more like a convention than a metaphysical fact. The reconstructed ship, assembled from original parts, has material continuity. Whether material continuity is a better criterion for identity depends on what you think ships fundamentally are. If they're patterns of organisation, material doesn't matter. If they're particular collections of stuff, patterns don't matter. Your intuition about which ship is the real one probably tracks some combination of these without being reducible to any single one. The harbour ship, maintained continuously, has been treated as real, inscribed in records, associated with the name. The reconstructed ship is made of the same pieces Theseus stood on. Social facts count. Material facts count. They point at different objects. Neither answer is obviously wrong. Both answers reveal something true about identity. The problem extends to nations. Is England the same country it was 1,000 years ago? Not a single person from that era remains. Laws, territory, language, and economy are unrecognizable. At every point you could say it was continuous with its past, but the end point seems entirely discontinuous with the beginning. Every criterion either allows too much change or requires too little. The harbour and the warehouse both have reasonable claims on the name. At what point does a thing become so different from what it was that it stops being the same thing? And who gets to draw that line? The unexpected hanging paradox. A judge tells a prisoner that he will be hanged at noon on one of the following 7 days, and that the execution will be a surprise. He will not know the night before which day it will be. The prisoner goes back to his cell and reasons carefully. The execution can't be on Friday, the last day. If he's still alive Thursday night, he'd know it had to be Friday, so it wouldn't be a surprise. But given that Friday's eliminated, it can't be Thursday either. If he survived Wednesday night and Friday's already eliminated, he'd know it had to be Thursday. Not a surprise. By the same logic applied step by step, he eliminates Wednesday, Tuesday, Monday, Sunday. The execution, he concludes, cannot happen on any day without violating the judge's promise of surprise. He relaxes. On Wednesday morning, the executioner arrives. The prisoner is hanged. He's completely surprised. His reasoning was valid at every step and produced a false conclusion. Something went wrong. What? Philosophers have been arguing about this since 1943, when it appeared in print, and they haven't converged on an answer. The problem has generated serious papers in logic, epistemology, and the theory of self-referential statements. Every proposed resolution spawns a counterexample. One approach says the problem is with the prisoner's knowledge about the judge's statement. The statement is self-referential in a subtle way. It says the prisoner won't know, which affects what he can deduce, which affects whether he'd know. The prisoner's conclusion that the hanging is impossible actually undermines his reasoning. If he's convinced it won't happen, then it can happen on any day and surprise him, restoring the possibility his reasoning was meant to eliminate. This is circular in an interesting way. The prisoner's confidence that the hanging is impossible is itself what makes the hanging possible. His certainty is self-defeating. But pointing this out doesn't fully dissolve the problem, because it's hard to say precisely what error the prisoner made without either accepting that the judge's statement was incoherent or that the prisoner's logic was somehow invalid, despite looking valid. A related approach says the statement is simply paradoxical, like the liar's sentence but embedded in a more complex scenario. Any statement that creates self-referential constraints about what the hearer can know may be inherently unstable. The prisoner correctly identifies an instability in the judge's statement, but misinterprets it as impossibility rather than paradox. The case connects to more general problems about knowledge, prediction, and statements about future epistemic states. When someone says you won't be able to figure this out, and you figure it out, have they been proven wrong? When someone says you'll be surprised, and you reason your way to the conclusion that nothing can surprise you, have you actually eliminated the possibility of surprise? Surprise depends on an epistemic gap, on not knowing. The prisoner tried to use knowledge to eliminate the possibility of surprise. What he may have demonstrated instead is that certain combinations of knowledge and prediction are self-undermining in ways that logic alone can't cleanly resolve. The executioner arrives on Wednesday. The prisoner who had concluded his own hanging was logically impossible is proven wrong in the most direct way available. What does it mean for a valid-seeming argument to produce a conclusion that reality simply overrides? Versions of the paradox appeared independently in the 1940s among Norwegian mathematicians and in logic puzzles about examinations. It was formalised more carefully in the 1950s as philosophers tried to identify exactly what kind of problem it was. The execution does happen, and the prisoner is surprised. The judge's promise is fulfilled. But the prisoner's reasoning concluded the promise couldn't be fulfilled. That's the structure of a paradox where the supposedly impossible thing happens anyway. Quine argued that the prisoner's reasoning was subtly invalid. The prisoner's conclusion that the execution is impossible relies on the assumption that the judge's promise will be kept. But the prisoner can't simultaneously assume the promise will be kept and deduce that it can't be kept. The reasoning is circular in a way that's easy to miss. Others have argued the paradox demonstrates genuine limits on what can be known. Certain self-referential claims about future epistemic states are inherently unstable. A judge can't coherently promise both that an event will occur and that it will be unknown the day before it occurs, at least not in certain logical environments. The promise makes a claim about knowledge that interacts with the prisoner's reasoning in a way that makes the claim unstable. The best response might be to say, the paradox reveals something about the limits of backward induction, the kind of reasoning that starts at the end of a sequence and works backward to the present. Backward induction works in many game-theoretic scenarios and produces clear solutions. Here it produces an impossible conclusion despite seemingly valid steps. That suggests backward induction has domain limits that are harder to specify than they appear. Logic said it couldn't happen. Wednesday it did. What does it mean for a logical conclusion to be simply overridden by what happens? The Crocodile Paradox. A crocodile steals a mother's child. The mother pleads for its return. The crocodile makes an offer. Return your child if and only if you correctly predict what I'm going to do. Tell me whether I'll give the child back or not. And if your prediction is correct, the child goes free. The mother thinks and then answers, you will not return my child. Now the crocodile has a problem. If it returns the child, the mother's prediction was wrong, and the crocodile's deal was to return the child only if the prediction was correct. The deal says don't return the child. But if it doesn't return the child, the mother's prediction was correct, and the deal says return the child. Every option the crocodile takes violates the conditions it set. The crocodile cannot honour its own promise, not because of any external obstacle, but because the logical structure of the promise makes honouring it impossible. This is an ancient paradox attributed to the Stoic philosophers, and it has the same architecture as the liar's sentence and Russell's paradox, a self-referential condition that generates a logical contradiction. The crocodile's offer refers to what the crocodile will do, and what the crocodile will do depends on the prediction, and the prediction depends on what the crocodile will do. The circularity creates a situation with no consistent resolution. One response is that the crocodile's offer was simply incoherent and should never have been made. A promise whose fulfillment conditions refer to predictions about the promise itself may be inherently unstable. The mother should have recognized this and not played. The game has no solution because the rules are self-defeating. But this response feels too clean for a paradox that's been generating argument for 2 millennia. The promise didn't sound incoherent when it was made. Conditional promises about future actions based on correct predictions are common and usually functional. What makes this one break down is the specific reference to the prediction being about the very action the promise governs. There's a legal version of this that's appeared in various forms. A defendant agrees to pay a lawyer only if the lawyer wins the case. The lawyer sues the defendant for the fee. If the lawyer wins, the defendant argues they don't owe the fee because the lawyer only wins if the defendant doesn't owe it. If the lawyer loses, the lawyer argues the defendant owes the fee under the original agreement. The paradox produced by adversarial contracts that refer to their own resolution isn't just philosophical. Courts generally solve these by imposing external rules that override the internal logic of the contract, declaring which party wins based on procedural grounds rather than trying to resolve the internal contradiction. That's a pragmatic solution, not a logical one. The paradox remains underneath the procedural ruling. What the Crocodile Paradox reveals is that natural language, and even carefully specified logical structures, can generate conditions that no possible state of the world satisfies. Paradoxes of this kind aren't just curiosities. They appear whenever self-referential conditions are embedded in promises, rules, or contracts. Legal systems, computer programs, and formal mathematical systems all have to handle cases where the rules refer to themselves in ways that create instability. The child is still with the crocodile. The logic offers no exit. The deal that was supposed to rescue the child instead trapped everyone in a circle that has no exit point. What do you do when a promise is logically impossible to keep? Not because circumstances changed, but because the promise itself contained the contradiction from the beginning. A formal system set up to prove its own consistency runs into exactly this. If it's consistent, it can't prove so from within. As Galileo showed, if it does prove its consistency, that's evidence it's inconsistent. The self-referential structure turns the question back on itself. The connection to the liar's paradox is direct. The crocodile's promise is essentially, I will return the child if and only if you correctly predict whether I will return the child. This is structurally similar to, this statement is true if and only if I will not return the child. In both cases, the condition refers to itself in a way that generates a circular truth value. Russell's type theory and later set theories like Zermelo-Frenkel were designed precisely to block these loops by imposing hierarchies. A statement at level n can refer to statements at level n-1, but not to itself, or statements at its own level. This blocks the liar and the barber, and in principle, the crocodile. But the blocking is achieved by restriction, not by resolution. The paradox still lurks at the boundary of the permitted zone. Ancient philosophers didn't have formal type hierarchies, so they wrestled with the crocodile directly. Chrysippus, the Stoic logician, reportedly found this kind of problem fascinating enough to devote significant work to it. Whether he found a satisfying solution is unclear because his writings on it don't survive. What survives is the problem, still generating argument after 2,500 years. The mother is waiting for her child. The logic has no exit. What do you do when the conditions you agreed to cannot be satisfied by any action you take? The Meno Paradox. How do you learn something you don't already know? Meno asks Socrates this question in Plato's dialogue, and the answer turns out to be stranger than the question. If you're looking for something, you have to know what you're looking for to recognize it when you find it. But if you already know what you're looking for, you've already found it. So learning seems impossible. You either already know what you're seeking, in which case inquiry is unnecessary, or you don't know it, in which case you wouldn't recognize it if you found it. This is the paradox of inquiry, sometimes called Meno's Paradox. And it sounds like a word game until you sit with it and realize it's pointing at something genuine about the structure of knowledge and how it grows. Socrates' answer in the dialogue was the theory of recollection. The soul has lived before and knows everything already. What we call learning is really remembering, drawing out knowledge that was always there but forgotten. He demonstrated this by leading an uneducated slave boy through a geometry proof, asking only questions, and the boy arrived at the correct answer. Socrates took this as evidence that the knowledge was always in the boy, waiting to be recovered. We don't believe in the pre-existence of souls the way Plato did, but the underlying structure of the problem remains. There's a real phenomenon being pointed at. When you're searching for an answer to a difficult question, you have to have enough structure in your search to recognize the answer when you encounter it. A completely arbitrary piece of information doesn't automatically announce itself as the thing you were looking for. Your prior knowledge shapes what counts as an answer. Consider learning a new language. You start with no knowledge of the vocabulary or grammar, but you're not starting from nothing. You have the structure of language itself, the concept of reference and predication, some implicit knowledge of how communication works, patterns learned from other languages, an ability to recognize sounds. You use existing knowledge to build a framework in which new knowledge becomes graspable. You never learn from complete ignorance. Thomas Kuhn noticed something similar about scientific revolutions. Normal science proceeds by solving puzzles within an accepted framework. The framework tells scientists what counts as a problem and what counts as a solution. When evidence accumulates that doesn't fit the framework, scientists tend not to recognize it as evidence against the framework, but as an anomaly or a measurement error. The framework shapes what the scientist is able to see. A radically new paradigm, one that would overturn the framework, is very hard to arrive at by inquiry within the old framework, because the old framework defines what counts as a meaningful question and a valid answer. Kuhn thought paradigm shifts happen more like gestalt switches than like ordinary inquiry, sudden reorganizations of the entire conceptual structure rather than gradual accumulations of new knowledge. This connects the Meno Paradox to a deeper problem about the limits of inquiry. Some things may not be discoverable by reasoning from within the conceptual structures you currently have. The framework of concepts you possess shapes what you're capable of learning. Learning isn't just accumulating new content. Sometimes it requires a structural change that can't be fully anticipated from the inside. What would you need to know already in order to discover the most important thing you don't know yet? There's a modern version of the Meno problem that appears in machine learning. A neural network is trained to recognize patterns in data. When it encounters a new image, it classifies it based on features it learned during training. If the new image contains features very different from anything in the training data, the network fails not by being wrong in a meaningful way, but by lacking the structure to see the question clearly. The network can't learn from inputs it has no framework to process. This is called distributional shift in engineering. The network can't inquire into inputs that fall outside its prior conceptual structure. Human cognition has the same limitation in subtler form. Karl Popper addressed the Meno problem from a different angle. Inquiry doesn't start from nothing, he argued, but it also doesn't start from knowledge. It starts from problems, from tensions between existing expectations and new observations. The prior knowledge isn't the answer or even the shape of the answer, it's the structure that makes a certain kind of gap visible. Learning happens at the gap. But Popper's answer doesn't fully dissolve the paradox, it just specifies where learning happens. The gap is still identifiable only from within an existing framework. What falls entirely outside the framework remains invisible, not as a gap, but as absence. Some things may be unlearnable not because they're difficult, but because they require a conceptual expansion that can't be achieved by inquiry from within the current framework. Whether there's a fact of the matter about what's on the other side of that expansion, and whether the expansion can be deliberately undertaken rather than stumbled into, is a version of the Meno Paradox that doesn't have a clean resolution. What do you need to already know in order to discover what you most need to learn? The Fitch Paradox. Start with something that sounds almost too modest to be interesting. Assume only this: every truth is knowable. Not that every truth is known, just that for any true statement, it's at least possible that someone could know it. There are no truths in principle beyond the reach of knowledge. That sounds like a minimal, humble claim about the openness of the world to understanding. Frederick Fitch proved in 1963 that this modest claim implies something far stronger. If every truth is knowable, then every truth is actually known, not potentially known. Known. The modest assumption about knowability collapses into omniscience. The proof is compact. Take any truth P that isn't currently known. The proposition P is true and unknown is itself a truth. By the knowability assumption, this compound proposition is knowable. So there's a possible situation in which someone knows that P is true and unknown. But knowing something requires it to be true. If you know that P is unknown, then P is unknown. But you also know that P is true, so P is known. Contradiction. P is both known and unknown in that situation. Therefore there can be no truth of the form P is true and unknown. Therefore all truths are known. The argument is logically valid. The conclusion is obviously false. Not every truth is known. So either the modest premise is false, some truths are in principle unknowable, or there's something wrong with how we're formalizing knowledge, or there's something strange happening with the logic of modal claims about knowledge. This matters beyond a logical puzzle. Verificationism, the philosophical view that only what's in principle verifiable is meaningful, relies on something like the knowability principle. If every meaningful claim is one that could in principle be known to be true or false, and if knowability collapses into actual knowledge, then verificationism implies that every meaningful truth is already known, which is absurd. Various technical responses have been proposed. Some restrict the knowability principle to apply only to certain classes of truths. Some modify the logic of knowledge claims to block the inference. Some argue the proof reveals that the principle needs to be stated more carefully, distinguishing between what's knowable by a single agent and what's collectively knowable, or between what's knowable at a time and what's knowable across all time. The Fitch Paradox has spawned a substantial literature in formal epistemology and modal logic. Every proposed resolution either accepts that some truths are unknowable in principle, which is a significant revision of the optimistic knowability assumption, or modifies the formal machinery in ways that seem somewhat ad hoc. What's most unsettling is the gap between the modest sound of the premise and the radical sound of the conclusion. If you start by assuming only that truth and knowledge are not permanently estranged, you arrive at a position that seems to require a God's eye view of everything. There might be true things that can never be known, not because we lack the technology or the intelligence, but because the very act of knowing them would change them into something false. What would a truth look like that destroys itself the moment it's known? The technical responses have mostly tried to restrict which truths the knowability principle applies to. Some restrict it to truths about the physical world, excluding truths about knowledge itself. Others distinguish between what's knowable by an individual and what's collectively knowable across all possible agents, and argue the proof only works for the individual case. Others revise the modal logic to use a different notion of possibility that blocks the inference. None of these has achieved consensus. The paradox remains active in the epistemological literature, not because it hasn't been worked on, but because the proposed resolutions each seem to smuggle in assumptions that are as controversial as the problem they solve. What's philosophically significant about the Fitch Paradox is that it shows how constraints on knowledge can interact with constraints on truth in unexpected ways. The connection between what's true and what can be known isn't transparent. A world in which every truth is knowable turns out to be a very different world from one in which every truth is merely accessible to possible inquiry. If knowing something changes it, if the act of knowing creates the thing known rather than discovering a pre-existing fact, then some truths might be fundamentally fragile. A truth about someone's unreflective inner state, for instance, might cease to be that truth the moment it becomes reflectively known. Whether such truths are genuinely unknowable in principle, or whether they're knowable at the cost of destroying what makes them true, is an open question. Science takes for granted that truths are discoverable, and that discovering them doesn't essentially change them. The Fitch Paradox suggests that if this is true, it's not guaranteed by logic alone. Some additional assumption about the independence of truth from knowledge is doing work, and that assumption might be wrong in some domains. What is the true thing about you right now that would stop being true the moment you knew it clearly? Every truth that depends on not being observed is fragile in this way. What else might dissolve the moment it becomes known? The Grelling-Nelson Paradox. Divide all adjectives into two categories. An adjective is autological if it describes itself. Short is a short word. English is an English word. Polysyllabic is polysyllabic. Adjectives that describe themselves are autological. An adjective is heterological if it does not describe itself. Long is not a long word. French is not a French word. Monosyllabic is not monosyllabic. Adjectives that fail to describe themselves are heterological. Now ask the question, is the word heterological itself heterological? If it is, it describes itself, which means it applies to itself, which means it's a word that does apply to itself. But heterological means doesn't apply to itself, so it doesn't apply to itself. Contradiction. If it isn't, it doesn't apply to itself, which means it's not heterological, which means it does apply to itself. Contradiction again. Kurt Grelling and Leonard Nelson identified this in 1908. Like Russell's paradox, which appeared around the same time, it shows that a certain kind of self-referential classification produces a logical contradiction. The word heterological is the set of all sets that don't contain themselves, dressed in linguistic clothing. The paradox is philosophically interesting for several reasons. One is that it arises entirely within natural language, using words and concepts that seem perfectly ordinary. Another is that it demonstrates how certain classification schemes generate edge cases that can't be consistently assigned to either category. A third is that it's resistant to the naive fix. The naive fix is to declare heterological, ill-formed or meaningless, but that's a desperate move rather than a principled one. Heterological is a grammatically correct word with a clear definition. The definition specifies a property that every adjective either has or doesn't. The paradox arises not because the word is confused, but because the classification system it belongs to generates a contradiction at a specific point. Russell's type theory handles this by forbidding self-reference. An adjective of type n can apply to adjectives of type n-1 but not to itself. Heterological is type 0, applying to type 0 adjectives. The predicate heterological would be type 1. Asking whether a type 0 adjective applies to itself is a type error. The paradox dissolves, but at the cost of imposing a hierarchy that feels somewhat artificial. Language, unlike formal logic, doesn't naturally come equipped with type hierarchies. Words apply to things, including themselves, and the grammar generally permits self-application. The Grelling-Nelson Paradox sits at the place where ordinary linguistic practice and logical consistency come apart. What's most disturbing about it is not the paradox itself, but the ease with which it's generated. A simple classification, into two exhaustive categories, applied to everything in a domain, produces a case with no consistent value. Completeness and consistency turn out to be harder to achieve simultaneously than they look. Is the sentence you're reading right now describing itself? And does the answer change anything about whether it's true? The autological-heterological distinction generates a puzzle even before you reach heterological. Consider autological itself. Is autological autological? If it is, it describes itself, meaning it's a word that applies to itself, which is exactly what autological means. So yes, autological is autological, consistently. No paradox there. But notice what this means. Autological is autological, and heterological is undecidable. The two categories were supposed to partition all adjectives, but one adjective falls into a genuine logical limbo. The partition fails to be complete in a consistent way. Now consider other adjectives that might approach the same territory. Is ambiguous ambiguous? It might be ambiguous whether a given word is ambiguous, which would make ambiguous ambiguous, but it's also clear that some words are unambiguously ambiguous, making the question itself ambiguous. Is polysemous polysemous? Meaning, does the word for having multiple meanings itself have multiple meanings? Arguably yes in both linguistic and logical senses. Is paradoxical paradoxical? These questions all dance around the same issue. Self-reference in natural language doesn't always produce clean answers. Sometimes it produces genuine indeterminacy that isn't resolvable by more careful analysis. The paradox is a linguistic relative of the set theoretic paradoxes. Russell's paradox appeared in 1901, Grelling and Nelson's in 1908. Both reveal the same underlying problem. Classification systems for the hypothesis. That seems like sensible scientific reasoning. Now consider the logically equivalent statement. Everything that's not black is not a raven. These two statements have identical truth conditions. Whatever makes one true makes the other true. Whatever would falsify one would falsify the other. They say the same thing in different words. Which means, if observing a black raven is evidence for all ravens are black, then observing a non-black non-raven should be evidence for everything. Not black is not a raven, which is evidence for all ravens are black. The apple on your desk is not black. It's also not a raven. By this logic, the apple is evidence that all ravens are black. Carl Hempel proposed this in 1945, and it's been generating argument ever since. It sounds absurd. You're sitting indoors with your apple, accumulating evidence about the colour of birds you've never seen, in habitats you've never visited, by virtue of eating fruit. Surely something has gone wrong. But identifying exactly what's gone wrong is harder than it looks. The logical equivalence is real. If observing confirms a hypothesis, it should confirm all equivalent formulations of the hypothesis, and the equivalence entails that the apple observation counts as evidence. Bayesian responses to the paradox are the most technically sophisticated. Yes, observing a non-black non-raven is technically evidence for all ravens are black, but an infinitesimally small amount of evidence given what we already know. We have rough estimates of how many ravens there are in the world, and how many non-black non-ravens there are. An apple observation updates the probability of the hypothesis by an amount so small it's negligible compared to the update from a black raven observation. The paradox is real, but the evidence is so weak it's practically meaningless. This Bayesian dissolution is technically adequate, but philosophically incomplete. It doesn't explain why the paradox feels wrong, It explains why the apple provides negligible evidence, but accepts that it provides some. Most people's intuition is that the apple provides no relevant information at all, not just very little. The deeper issue is about what we mean by confirmation. Is confirmation a purely logical relation between evidence and hypothesis? Or does it depend on background knowledge, on relevance, on how we've framed the inquiry? If it's purely logical, the apple confirms the hypothesis. If background knowledge and relevance matter, we need an account of what makes evidence relevant, rather than just logically consistent with a hypothesis. The Raven Paradox lives at the boundary between the logic of confirmation and the pragmatics of scientific inquiry. Science works by seeking specific evidence, by designing experiments to test hypotheses, by using background knowledge to determine what's relevant. The paradox shows that if you strip all of that away and just ask about logical confirmation, strange things emerge. Does the fact that you're not currently on fire confirm the hypothesis that all unicorns can fly? Scientific confirmation isn't just logical consistency with a hypothesis. It involves something more, something like relevance or informativeness. A red apple isn't relevant to raven coloration in any ordinary sense, even if it's logically consistent with a hypothesis about ravens. What counts as evidence depends on background assumptions. Whether an apple observation is evidence about ravens depends on the theoretical framework. Pure logical confirmation theory strips away the framework and finds that apples confirm raven hypotheses, which suggests it's missing something important. The Raven and Grue paradoxes together show that the logic of confirmation is substantially underdetermined. Evidence doesn't confirm hypotheses in a purely logical way. Background assumptions, pragmatic considerations, and the history of successful use of certain concepts all play roles that formal logic doesn't capture. Which of your current confident beliefs might be the equivalent of apple evidence, logically consistent but not actually informative about what you think it is? Popper built his philosophy of science on this asymmetry, arguing that science advances through falsification. Under that view, the apple isn't evidence for the raven hypothesis at all, because it's not a genuine test. Only something that could have falsified the hypothesis counts as real evidence. Does the apple tell you anything, or does it only seem to? Scientific confirmation isn't just logical consistency, it involves relevance and informativeness. Background knowledge determines which observations are relevant to which hypotheses, and that background is what makes raven confirmation about ravens rather than about every non-black thing. Does the fact that you're not currently a raven confirm anything about the ravens you've never seen? The paradox has been running since 1945 without resolution to everyone's satisfaction. Which of your confident beliefs might be the equivalent of apple evidence, logically consistent with what you're confident about, but not actually tracking it? The lottery paradox. A fair lottery has 1 million tickets. One will win. You hold ticket 471,832. The probability that your ticket loses is 999,999 out of 1 million. That's high enough that it seems reasonable to believe your ticket will lose. You're not certain it will lose, but it's rational to believe things that are highly probable. Now apply the same reasoning to every other ticket. For each ticket in the lottery, the probability that it loses is 999,999 out of 1 million. It's rational to believe each one will lose. By the same standard of rationality, you believe ticket 1 will lose, ticket 2 will lose, and so on through all million tickets. You now rationally believe that every ticket will lose, but exactly one ticket must win. Your rational beliefs are jointly inconsistent. You believe each individual statement, while the conjunction of all of them is necessarily false. Henry Kaiberg introduced this in 1961, and it's remained philosophically significant ever since. The paradox exposes a tension at the heart of rational belief. We hold beliefs based on high probabilities. We accept that rational beliefs should be consistent with one another. But if you apply the high probability standard to each case individually, you accumulate a set of beliefs that are collectively inconsistent. One response is to raise the threshold for rational belief. Instead of accepting beliefs based on 999,999 out of 1 million probability, require certainty. Only believe what you know for certain. But this is too demanding. Almost everything we ordinarily believe falls short of certainty. Science works with probabilities. Daily life depends on probabilistic reasoning. Requiring certainty makes rational belief nearly impossible. Another response is to deny that rational beliefs must be closed under conjunction. Believing each of A, B, and C individually doesn't commit you to believing A and B and C all at once. But this seems to allow a kind of compartmentalization that contradicts how logical reasoning is supposed to work. If you believe each premise of an argument, shouldn't you believe the conclusion? A third response says the lottery paradox shows that high probability is not sufficient for rational belief. Something else is required, perhaps knowledge rather than mere high credence, or perhaps the right kind of causal connection to the truth. This is epistemologically interesting, but doesn't specify what the missing ingredient is. The paradox has a companion called the Preface Paradox. An author writes a careful non-fiction book and includes a preface saying that despite best efforts, the book surely contains some errors. The author believes each statement in the book and also believes the book contains errors. Both beliefs are rational, but they're jointly inconsistent. Every careful thinker who believes many things is in the same position. No large set of beliefs is guaranteed to be error-free. Acknowledging this is epistemically virtuous, but it means believing, at the level of the collection, that something you believe is false, without knowing which one. Somewhere in your beliefs, something is probably wrong. Does knowing that change how you hold the rest of them? The lottery paradox connects to broader questions about the relationship between belief and action. If you believe each ticket will lose, you should act on that belief. If offered a chance to buy ticket 471,832 back for face value, you'd decline, having already written it off. But you'd presumably buy a lottery ticket if offered one for less than its expected value, which seems to assume you give some credence to winning. Your beliefs and your actions express different probabilistic stances toward the same situation. This suggests that belief, as a flat on or off state, might not be the right representation of our epistemic states in probabilistic environments. Degrees of belief, credences, might be more accurate. Rather than either believing or not believing your ticket will lose, you have 999,999 out of 1,000,000 credence that it will. That's very high credence, not outright belief. Moving to credence rather than belief avoids the lottery paradox, because you simply don't form the outright belief that each ticket will lose. You have high credence that each will lose, but you also acknowledge that one must win. The credences are consistent. Each ticket has 999,999 over 1,000,000 credence of losing and 1 over 1,000,000 credence of winning, and the credences sum correctly. But moving entirely to credences creates a different problem. We ordinarily believe things, assert things, act on things as if they were true rather than merely probable. If you tell someone your flight departs at 9, you're not communicating a credence distribution over departure times. Ordinary discourse seems to require something more like outright belief than credence. The relationship between the quantitative world of probabilities and the binary world of assertion, belief, and action hasn't been resolved. The lottery paradox sits at the fault line between them, showing that the binary world has cracks that the quantitative world can see through. What do you actually believe? And what do you merely have high credence in? And can you tell the difference from the inside? Somewhere in the collection of beliefs you hold with high confidence, something is probably false. The lottery tells you this is inevitable. What it doesn't tell you is which one. Russell's paradox. Consider the set of all sets that don't contain themselves. Most sets don't contain themselves. The set of all apples doesn't contain itself. It contains apples. The set of all odd numbers doesn't contain itself. So the set of all sets that don't contain themselves is a reasonable sounding thing to define. Now ask, does this set contain itself? If it does, it's a set that contains itself. So by definition, it shouldn't be in the set of sets that don't contain themselves. Contradiction. If it doesn't, it's a set that doesn't contain itself. So by definition, it should be in the set of all sets that don't contain themselves. Contradiction. Bertrand Russell identified this in 1901, and it was devastating. At the time, mathematicians were trying to establish rigorous foundations for all of mathematics using set theory. Gottlob Frege had just published the second volume of his Grundgesetze, a major work attempting to derive arithmetic from pure logic and set theory. Russell sent him a letter describing the paradox. Frege recognized immediately that it destroyed a central axiom of his system. He wrote in the appendix to the already printing second volume that he had discovered the foundation had been shaken. What Russell's paradox showed was that naive set theory, the intuitive idea that you can form a set from any coherent description of a collection, was inconsistent. The description all sets that don't contain themselves is coherent sounding, and yet no consistent set can satisfy it. The resolution required rebuilding the foundations of mathematics. Zermelo-Fraenkel set theory, the framework most mathematicians now use, carefully restricts which sets can be formed. You can't form a set from an arbitrary description. You can only form a set by specifying a subcollection of an existing set. This prevents the universal sets that generated the paradox. But the restriction is a workaround, not an explanation. The intuition that any coherent description defines a collection turns out to be wrong, but it's not obvious why. The descriptional sets that don't contain themselves sounds perfectly coherent. Pointing out that it generates a contradiction tells us the description is problematic, without telling us what went wrong at the conceptual level. Different people have different reactions to this. Some say it shows that the concept of a set was never well defined in the first place, that we were working with a confused notion that happened to work in familiar cases. Others say it shows that self-reference needs to be restricted at a deep level, that anything defined in terms of itself is potentially dangerous. Others treat it as a technical problem that was solved by the axioms. What's genuinely unsettling is that mathematics, which is supposed to be the domain of pure certainty, was built on a foundation that turned out to be internally inconsistent. The fix was found, but the fact that it was needed at all suggests that even the most careful and rigorous domains of human thought can contain hidden contradictions that only surface under sufficient pressure. If a collection of all the things that aren't members of themselves can't coherently exist, what does that say about the things that seem to define themselves by what they exclude? The ramifications of Russell's paradox extended far beyond mathematics. Frege's logicist project, the attempt to derive all of mathematics from pure logic, was fatally undermined. The project wasn't just technically incomplete, its foundations were internally inconsistent. Mathematics, which had prided itself on certainty above all other disciplines, was shown to have been built on shaky ground. The response was to rebuild the foundations more carefully. Zermelo-Fraenkel set theory restricts set formation by requiring that sets be built up iteratively from simpler sets rather than defined directly from arbitrary descriptions. The restriction prevents Russell's construction from getting off the ground. You can't form the set of all sets that don't contain themselves because there's no prior set containing all sets to take a subset of. But the restriction has always felt like a workaround rather than a resolution. The restricted theory works. It avoids the paradoxes. It provides a foundation for essentially all of mathematics. What it doesn't do is explain why the naive principle that any coherent description defines a set fails at this particular point. The restriction is imposed because it avoids paradox, not because it reflects a deep conceptual insight about what sets are. Gödel's incompleteness theorems in 1931 showed that any sufficiently powerful formal system can't prove its own consistency. The dream of establishing mathematical certainty from pure logic was definitively ended. What we have instead is mathematics built on axioms that are chosen because they avoid known paradoxes and produce useful results, not because we have independent grounds for their truth. The foundations of mathematics are chosen pragmatically. This is a very different situation from what mathematicians believed they were in before Russell's letter to Frege. The set of all sets that don't contain themselves doesn't exist. What does exist is a formalism designed to exclude it, without a complete explanation of why it needs to be excluded. What else might we be assuming coherent that turns out to generate contradictions under sufficient pressure? The Berry Paradox. Consider the phrase, the smallest positive integer not definable in fewer than 14 words. Count the words in that phrase, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 words. So this 14-word phrase about integers not definable in fewer than 14 words has just defined a specific integer in 13 words. But if it's definable in 13 words, it's not the smallest positive integer that can't be defined in fewer than 14. So the phrase fails to define what it claims to define. And if it fails to define any integer at all, then there is a smallest positive integer not definable in fewer than 14 words. And you've just found a phrase that defines it in 13 words. Around it goes. G.H. Hardy and Bertrand Russell discussed this. It was apparently suggested by George Berry, a librarian at the Bodleian, which is why it carries his name despite his being somewhat peripheral to the academic conversation it generated. Like the liar's paradox, it's a self-referential statement that undermines itself. Unlike the liar's paradox, it operates through the concept of definability rather than truth. The paradox shows that definability, applied to itself, generates contradictions. Russell's solution type theory handles this by placing definitions in hierarchies. A definition at level n can refer to objects definable at level n-1, but not to objects at level n or higher. A phrase about integers not definable in fewer than 14 words is a definition at some level, and the integers it refers to must be at a lower level. The phrase can't define something at the same level as itself. This blocks the paradox but requires you to accept the type hierarchy as a genuine feature of definitional language rather than an artifact imposed to avoid trouble. Whether the hierarchy reflects something deep about the structure of meaning or is a technical workaround is contested. The Berry paradox also connects to deeper questions in the theory of computation. Turing's work on the halting problem uses a related structure. He showed that no Turing machine can decide in general whether an arbitrary program will halt by constructing a machine that would have to solve its own halting problem. The self-referential structure is the same, a computation that would be defined by the output of a computation that would have to refer to itself. Gödel's incompleteness theorems use yet another version. Gödel constructed a sentence in arithmetic that says of itself that it can't be proved. The self-reference is encoded through numbering of formulas rather than through English phrases, but the underlying structure is the Berry paradox translated into arithmetic. What these share is the discovery that self-reference at the level of definition, proof, or computation creates instabilities that can't be resolved by more careful definition or more powerful machinery. The paradoxes aren't mistakes in reasoning. They're symptoms of a structural feature of any sufficiently expressive system. In how many words could you describe something that cannot be described? The connection between Berry and Gödel runs deep. Gödel encoded mathematical statements as numbers, allowing arithmetic to talk about itself. He then constructed a statement that said of its own Gödel number that the statement with that number is unprovable. This is the Berry paradox in arithmetic, a statement that defines itself by reference to what can be defined within the system. Gödel's incompleteness theorems showed that any consistent formal system powerful enough to express basic arithmetic contains true statements that can't be proved within the system. The proof works by constructing a Berry-type self-referential statement. The undecidability of heterological in Grelling's linguistic paradox is a natural language version of the same result. These connections suggest that the paradoxes aren't isolated curiosities. They're manifestations of a single underlying phenomenon. The limits of formal systems when they try to turn their own tools on themselves. Language trying to define language from within. Logic trying to capture logic from within. Arithmetic trying to prove arithmetic from within. In each case, self-reference creates instabilities at the boundary. The practical upshot for mathematics and logic is significant. There are things that can't be proved or decided by any formal system, not because they're difficult or unknown, but because of a structural feature of how formal systems work. This is a permanent feature, not a temporary limitation. No more powerful formal system resolves it, because more powerful systems create more powerful self-referential statements that fall outside their scope. For natural language, the upshot is less formally precise, but equally significant. Natural languages contain their own semantics, which means they can generate Berry-type constructions at will. The instabilities are managed pragmatically, by interpreting charitably, by context, by ignoring problematic cases. But the formal paradoxes are always lurking under the surface. Words define other words. At the edge of every definition, there's a possibility of a loop that points back at itself with no clear resolution. If the thing you're trying to define slips away the moment the definition closes, what does that tell you about the thing? The liar paradox. This statement is false. If the statement is true, then what it says is the case, which means it's false. If it's false, then what it says isn't the case, which means it's not false, which means it's true. Neither assignment of truth value is stable. Ancient Greek philosopher Epimenides said all Cretans are liars. He was a Cretan. Eubulides of Miletus sharpened this into the liar's paradox in the 4th century BCE. It's been generating serious philosophical and logical work ever since, making it one of the longest-running open problems in the history of thought. The paradox seems simple enough to dismiss. Just say liar-type statements are meaningless. Self-referential nonsense that shouldn't be taken seriously. Problem is, this statement is false doesn't look grammatically confused. It's a complete sentence with the right syntactic structure. Ruling it out requires a principled account of what makes it semantically defective, rather than just saying it's weird. Various accounts have been proposed. Some say sentences require determinate reference to be meaningful, and liar sentences fail to refer to anything determinate. Some say truth predicates create a hierarchy, with sentences about sentences belonging to a higher level than the sentences they're about. And liar sentences violate this hierarchy. Some say the concept of truth for a language has to be defined outside that language in a meta-language, and sentences that try to apply truth to themselves are just outside the scope of the predicate they're using. Each of these works technically in formal systems. Each has felt to many philosophers like it's resolving the paradox by legislative fiat, rather than by identifying what's actually wrong with a liar sentence. Alfred Tarski's treatment in the 1930s was the most influential. He showed that if a language contains its own truth, predicate, and allows arbitrary self-reference, it will contain liar-type sentences. The solution is to define truth for a language only in a richer meta-language. This works, but implies that natural language, which does seem to contain its own truth predicate and does allow self-reference, is either inconsistent or needs to be regimented in ways that change what it is. There are solutions that accept the paradox rather than dissolving it. Dialetheism, developed by Graham Priest among others, accepts that some sentences are both true and false. The liar sentence is one of them. Rather than changing the logic to avoid the contradiction, dialetheism changes logic to tolerate some contradictions. This is unsettling to most logicians, but has a rigorous technical development and has been seriously defended. What makes the liar special among paradoxes is how close to ordinary language it sits. You don't need a physics lab or a philosophy seminar to construct one. 4 words, and you have a statement that neither truth nor falsity can settle. If you can't say whether it's true or false, what kind of thing is it? The liar has received serious attention from logicians, linguists, and philosophers for 2.5 millennia because no resolution has achieved consensus. Each proposed solution either requires modifying logic in ways that seem ad hoc, restricting language in ways that seem arbitrary, or accepting consequences that seem worse than the original paradox. Tarski's hierarchy of metalanguages works formally, but implies that truth is always relative to a level of language, never absolute. English has a truth predicate, but it's truth for English minus certain self-referential sentences. And there's a metalanguage that handles truth for all of English, and so on. This regress never reaches a level at which truth is simply defined. It pushes the problem upward without resolving it. The dialetheist response, accepting that some sentences are both true and false, requires revising classical logic to tolerate contradictions. The revised logic must be weaker than classical logic in ways that prevent the contradiction from spreading to all sentences. This is technically achievable. Whether it's philosophically acceptable depends on whether you think some true contradictions are genuinely possible, or whether contradiction is always a signal of error. What the liar suggests about truth is important. Truth is supposed to be a transparent meta-level concept. To say P is true is just to say P. The liar sentence exploits this transparency to create a self-referential loop. If truth were entirely opaque, if saying P is true were entirely different from saying P, the liar sentence couldn't be constructed. The transparency of truth, which seems like a virtue, is part of what creates the problem. Natural language has been living with the liar for 2.5 millennia and hasn't collapsed. Speakers manage to communicate, reason, and make claims about truth without regularly encountering the liar sentence and freezing. The paradox is real, and the formal solutions are imperfect, but language seems to have a robustness that formal theories of language don't fully explain. This statement is false is 4 words. The instability they create has no clean exit. If something can't be called true and can't be called false, what is it? This statement has been waiting 2.5 millennia for logic to catch up to it. Logic is still working on it. The statement is not waiting. The Barber Paradox. A barber in a small town shaves all the men in town who don't shave themselves, and only those men. Does the barber shave himself? If he does, he's a man who shaves himself, so according to the rule he shouldn't be shaved by the barber. But he is the barber. Contradiction. If he doesn't, he's a man who doesn't shave himself, so according to the rule, he should be shaved by the barber. He is the barber. Contradiction. Bertrand Russell introduced this as a simplified version of his more technically demanding paradox about sets. The Barber Paradox is Russell's paradox in everyday clothes, designed to make the abstract problem concrete and vivid. The set of all men who don't shave themselves corresponds to the set of all sets that don't contain themselves. The barber's relationship to the set of men he shaves corresponds to a set's membership in the problematic set. The resolution to the Barber Paradox is straightforward in a way that the set theoretic version isn't. The answer is, no such barber can exist. The description specifies a barber whose situation is logically impossible. Not physically improbable or practically difficult to arrange, logically impossible. The town and its barber are ruled out by logic before you even check whether anyone's home. This seems clean. Define something incoherent, get no coherent object. The set theoretic version is harder because sets are supposed to be definable by coherent descriptions, and all sets that don't contain themselves sounds more coherent than any barber who shaves all and only the non-self shavers. The Barber Paradox helps you see why the set is also incoherent by making the logical structure viscerally clear. What's interesting about why the barber is impossible is that it's not self-contradictory in the way that round squares are. The barber can exist as a physical person. The rule he operates by can be articulated clearly. It's the combination of the rule with the barber being a member of the class the rule governs that creates the problem. Self-reference within a defining rule generates impossibility. This has practical analogues. Consider a regulation that says all rules must be registered, including this one. Whether this rule is registered before or after the regulation passes determines whether it creates a paradox. Systems of rules that govern themselves face this problem regularly. Constitutional provisions that govern how constitutions can be amended. Legal procedures that specify how legal procedures can be challenged. Meta rules that specify what rules can be made. These don't always produce paradoxes, but they create vulnerabilities to paradox at the point where the rules loop back on themselves. Real legal systems handle this with precedents, hierarchies, interpretive traditions, and pragmatic workarounds that prevent the formal paradox from materializing. But the formal paradox is still there underneath, contained rather than resolved. The barber lives in a logical impossibility. The town exists only in thought experiments. What happens when a rule tries to govern the rule itself? The Barber Paradox also illuminates something about the nature of existence proofs in mathematics. Mathematicians sometimes define objects by specifying properties they must satisfy, then ask whether any object with those properties exists. The answer is not always yes. Some specifications have no satisfying instance. The Barber specification is one. Whether a given specification has any satisfying instance depends on the internal logic of the specification. If the specification is self-contradictory, like the barber's, nothing satisfies it. If the specification is consistent, something might or might not satisfy it, depending on the domain. This matters for the foundations of mathematics. Many mathematical objects are defined by their properties. The question of whether objects with those properties exist is separate from, and logically prior to the question of what those objects are like. The Barber Paradox teaches this lesson vividly by presenting a definition that's plausible sounding, but internally contradictory. In set theory, Russell's paradox shows that the definition all sets that don't contain themselves doesn't pick out any set. The definition has the same structure as the barber's rule. No set satisfies it. The barber is impossible for the same reason the problematic set is impossible. Russell used the barber to make this visible, because most people have a clearer intuition about barbers than about set membership. What makes the paradox pedagogically useful is the way it demonstrates that existence can fail quietly. You can define something, give it a name, start reasoning about it, and only discover later that nothing satisfies the definition. The failure isn't always obvious. The barber's rule sounds like it could describe a real barber. It takes a specific question, does the barber shave himself, to reveal the inconsistency. This applies to conceptual definitions generally. Concepts can seem coherent under casual inspection, and turn out to be incoherent when pressed. Philosophy is partly the practice of pressing on concepts until they either hold firm or reveal their cracks. The barber doesn't exist and can't. What else have you defined that might not? A rule that governs itself is always standing on the edge of this. What does it mean for a rule to try to shave itself? The Sorites Paradox. Take a heap of sand. Remove one grain, still a heap. Remove another, still a heap. Keep going one grain at a time. At each step, removing one grain doesn't turn a heap into a non-heap. And yet at the end of this process, you have one grain. Or no grains, either way, not a heap. The paradox is ancient, attributed to Eubulides of Miletus in the 4th century BCE. The word Sorites comes from the Greek for heap. And it's not really about sand. Sand is just the clearest example of a problem that appears everywhere in human conceptual life. Take bald. If someone has a full head of hair and you remove one hair, they're not suddenly bald. If removing one hair never turns someone bald, then by induction, no matter how many hairs you remove, no one becomes bald. But people manifestly do become bald as their hair thins. The argument that no single hair removal makes someone bald, repeated enough times, leads to a conclusion that contradicts experience. The same structure applies to tall and short, rich and poor, young and old, red and orange, hot and cold, many and few, alive and dead, sober and drunk. For any predicate that admits of gradations, the Sorites argument seems to show that the predicate can never determinately apply or fail to apply. One response is epistemicism. There's a precise threshold, we just don't know where it is. At some specific number of grains, the pile becomes a heap. At some specific hair count, a person becomes bald. The thresholds exist but are unknowable. This preserves classical logic but requires us to accept that our words have perfectly sharp meanings we can never discover. Another response is to change the logic. In fuzzy logic, predicates have graded truth values. A pile of 1,000,000 grains is definitely a heap. A pile of 10 grains is mostly not a heap. A pile of 50,000 grains is somewhat a heap. There's no sharp transition, just a gradient. The predicate heap is true to different degrees at different points. A third response is contextualism. The threshold shifts depending on context. What counts as a heap at a construction site differs from what counts at a jeweler's. The predicate is not vague, it's context sensitive. And the context specifies a precise threshold appropriate to the current use. None of these is obviously right. Epistemicism requires mysterious, sharp thresholds we can never locate. Fuzzy logic requires changing the fundamental logic of truth and falsity. Contextualism makes precise what actually seems genuinely vague. The Sorites paradox matters beyond sand and hair because vagueness is pervasive in law, medicine, ethics, and science. At what developmental stage does a fetus acquire the morally significant properties that determine how it should be treated? At what point does a treatment count as torture rather than harsh interrogation? At what ratio does a corporation become a monopoly? These aren't just hard empirical questions. They're hard because the predicates themselves don't have sharp edges. How many grains of sand does it take to make a heap? And what happens to logic when the question can't be answered? There's a version of the Sorites paradox that applies to the concept of species and drives an evolutionary problem. At what point in the gradual process of evolution does a new species begin? If we go back through any living organism's ancestry, we find a continuous chain of individuals, where adjacent individuals were all members of the same population and capable of interbreeding. At no point in that chain is there a sharp transition, where parent is one species and offspring is another, and yet species manifestly differ. Dogs and wolves are distinct species, even though there's a continuous lineage connecting them to common ancestors that were neither. The Sorites problem in evolutionary biology is that species categories, which biologists use constantly and which have genuine utility, can't be grounded in sharp natural kinds. The borders are drawn by observers based on practical considerations. Philosophers of biology have argued about whether species are natural kinds, historical individuals, or something else entirely. The Sorites problem makes clear that if species are natural kinds with sharp membership criteria, then the criteria need to be specified in a way that allows sharp transitions, which evolution doesn't produce. If species are historical individuals with fuzzy boundaries, then the boundaries are conventional rather than natural. This doesn't mean species aren't real, it means real things can have fuzzy boundaries, and that matters for how we think about the concepts we use to organize the world. Many of the categories we treat as natural and sharp, legal, medical, ethical, political, maybe like species, genuinely useful, tracking real patterns in the world, but without the sharp edges we implicitly assume when we reason about them formally. Law treats the question of when someone is dead as having a precise answer. Medicine requires this for practical reasons, but the biological process of dying is gradual, and the choice of where to draw the line is partly conventional. The Sorites sits at the boundary of every concept that applies to a continuum. At what point does one grain of sand change everything? And is there any grain at which the answer matters more than the others? Buridan's ass. Imagine a perfectly rational donkey placed at the exact midpoint between two identical bales of hay. Both bales are the same size. Both are equally fresh. Both are exactly the same distance away. The donkey is hungry. It has no reason to choose one bale over the other because the situation is perfectly symmetric. A perfectly rational agent chooses based on reasons. No reasons favour one option over the other. Therefore, the donkey cannot choose. It stands there, equidistant between two identical sources of food, and starves to death. Jean Buridan's name is attached to this paradox, though he probably didn't originate it. Aristotle discussed a version involving a man equally hungry and thirsty equidistant between food and drink. The medieval philosophical tradition elaborated it, and Buridan's ass has become the canonical formulation. The paradox is philosophically interesting because it probes the relationship between rational choice and symmetric situations. Most decision theory assumes that rational agents can always choose, but decision theory also assumes that choices are based on reasons. If there are no reasons to favour one option, and if reasons are what choices are based on, then no choice should be made. The donkey is perfectly rational, and therefore perfectly paralysed. One response is that rational agents can break ties arbitrarily. When two options are equally good, it's rational to just pick one, even randomly. This seems obviously right practically, but it's philosophically uncomfortable. Arbitrary choice is not reason-based choice. If rational choice is defined as reason-based choice, then arbitrary tie-breaking isn't rational in the relevant sense. It's irrational, outside the scope of rationality rather than consistent with it. Another response is Leibniz's. He argued that truly symmetric situations are metaphysically impossible because of his principle of the identity of indiscernibles. Two things that are identical in all properties are not two things but one. The two bales of hay cannot be genuinely identical because they exist at different locations, and location is a property. Therefore, there's always some reason to prefer one over the other, even if that reason is purely spatial. Leibniz's solution saves rationality, but seems to change the problem rather than solve it. Even if the bales differ in some undetectable way, the difference is epistemically inaccessible to the donkey. From the donkey's perspective, the situation remains symmetric. Whether the metaphysical symmetry or the epistemic symmetry is what matters for rational choice is itself a substantive question. The problem connects to quantum mechanics in an interesting way. In quantum systems, certain symmetries are exact and not just approximate. Identical particles are genuinely indistinguishable, not just practically but in principle. Whether quantum entities face a version of the donkey's problem, and whether quantum probability is a way of resolving symmetric situations without breaking the symmetry, is a genuine open question in the philosophy of physics. The donkey starves at the exact centre. Its perfect rationality is what kills it. What does this suggest about the relationship between rational choice and the inability to decide? The donkey problem has a modern restatement in decision theory called the problem of indifference. Standard expected utility theory says rational agents maximize expected utility. When two options have equal expected utility, the agent is indifferent between them. But indifference is not a choice. At some point, the agent must act. Decision theory tells you to be indifferent, but doesn't specify what to do with the indifference. Some decision theorists say you should randomize between equal options, treating them as interchangeable. But true randomization requires a source of randomness, and a perfectly rational agent with perfect knowledge of a perfectly symmetric situation might not have access to one. The symmetry would need to be broken from outside the agent's deliberation by some feature of the world that breaks the symmetry. The agent would then choose the option on the favoured side, but that's not choosing based on reasons either. That's choosing based on what happens to be slightly more accessible. The real-world version of the donkey problem is the phenomenon of decision paralysis. Faced with many options of roughly equal value, people sometimes postpone decisions indefinitely rather than choose. This is usually treated as a failure of rationality. But Buridan's ass suggests it might be an accurate response to genuinely symmetric situations. If there's no reason to prefer one option, there's no way to choose without abandoning reason-based choice. Whether this matters practically depends on how often genuinely symmetric situations arise. In real life, options are almost never exactly equal. But they can be close enough that the marginal differences don't seem to justify a strong preference, and the result is something functionally similar to the donkey's paralysis. The donkey starves at the exact centre because it is perfectly rational. Imperfect rationality, a bit of arbitrariness, a coin flip, would save it. What does it mean that perfect rationality is fatal in a symmetric world? The perfectly rational donkey starved because rationality, pushed to its limit, has no mechanism for escape from symmetry. The Coastline Paradox. How long is the coastline of Britain? The answer depends entirely on how you measure it. If you walk around the coast with a measuring stick 100 kilometers long, you get one number. Use a stick 10 kilometers long and follow more of the inlets and headlands, and you get a larger number. Use a stick 1 meter long and trace every rock and crevice, and you get a still larger number. Use a millimeter stick and follow the contours of individual sand grains, and the number explodes. Continue down to the molecular level, and the coastline appears to be, for practical purposes, infinite. Lewis Fry Richardson documented this in the 1950s, and noticed that different countries' official measurements of their shared borders often differed significantly, not from error, but from different implicit choices of measurement scale. He found that the relationship between the measured length and the measurement scale followed a power law. As the scale decreased, the measured length increased, and it did so in a systematic way that depended on the fractal dimension of the coastline. Benoit Mandelbrot developed this insight into fractal geometry in the 1960s and 1970s. A fractal is a structure that shows self-similarity across scales, roughly the same level of detail and complexity, no matter how far you zoom in. Real coastlines aren't true mathematical fractals, because at some small scale, they're made of discrete physical objects like rocks and sand grains. But over many orders of magnitude of scale, they behave like fractals, and the measured length continues to increase as measurement scale decreases. The practical upshot is that coastline length is not a well-defined quantity. There is no objectively correct answer to how long a coastline is. Every answer is relative to a measurement scale, and the choice of scale is arbitrary. Different purposes call for different scales, and the lengths at different scales are incommensurable. This matters beyond geography. The same measurement problem appears in any physical boundary between two regions of space. The perimeter of a lung, the surface area of a protein, the boundary of a cloud, the interface between two geological formations. All of these have dimensions that depend on measurement scale, and all of them have no scale-independent, correct value. Finance is another domain where this matters. Market price series have fractal-like properties. The distribution of price changes looks similar at different timescales. Models that assume smooth price processes systematically underestimate the probability of large moves because they don't account for the fractal structure of actual price behavior. Several financial crises have had, as a contributing cause, models that assumed smooth curves in a world of fractally rough ones. The lesson of the Coastline Paradox isn't that measurement is impossible. It's that the implicit assumptions built into a question determine what answers are possible. How long is the coastline of Britain presupposes that coastlines have lengths. They do, for every choice of scale. They don't have a length, independent of scale. How many of the questions you treat as having definite answers depend on assumptions about scale that you haven't examined. The fractal structure of natural objects extends to objects in biology and physiology. The branching of blood vessels follows a fractal pattern that allows efficient delivery of blood to every cell in the body while minimizing the total length of the vascular network. The branching of the airways in the lungs has a similar structure. Neurons in the brain branch fractally. The geometry isn't accidental. It seems to be a solution to optimization problems, a way of packing complexity efficiently into limited space. What the Coastline Paradox reveals about these biological structures is that their measured surface areas and lengths are also scale dependent. The surface area of a lung increases as you measure it at finer scales, because the airways branch at every scale and each level of branching adds more surface. Whether there's a meaningful biological notion of total lung surface area that doesn't depend on the scale of measurement is questionable. At the molecular scale, the surface area becomes essentially ill-defined. Whether the cell membrane of a neuron is a smooth surface or has features at every scale down to the molecular is both a question of measurement and a question about what kind of object a cell membrane fundamentally is. The Coastline Paradox is ultimately a lesson about the relationship between mathematical models and physical objects. We model coastlines as curves, mathematical objects with one-dimensional structure. Real coastlines are three-dimensional physical objects at every scale. The mismatch between the model and the object produces the paradox. Choosing a model is always choosing a scale, a level of abstraction, a grain of detail below which we don't look. Different questions require different scales. Navigation needs a very different level of detail than ecology, which needs a very different level than geology. The coastline has a different length for each of these purposes, and none of those lengths is more correct than the others. What other questions do you treat as having determinate answers that might dissolve when you examine what level of detail you are implicitly assuming? Galileo's paradox of infinity. The natural numbers go on forever. 1, 2, 3, 4, and so on without end. The perfect squares are a subset of the natural numbers. 1, 4, 9, 16, 25, and so on. There are clearly more natural numbers than perfect squares, because most natural numbers aren't perfect squares. Between 1 and 100, there are 100 natural numbers, but only 10 perfect squares. And yet you compare every natural number with exactly one perfect square. 1 with 1, 2 with 4, 3 with 9, 4 with 16, and so on forever. Every natural number gets paired with n squared. Every perfect square gets paired with exactly one natural number. No natural number is left without a pair. No perfect square is left without a pair. If you compare the elements of two collections 1 to 1 with no leftovers, the collections have the same size. That's what it means to have the same number of things. By this definition, there are exactly as many perfect squares as there are natural numbers. Galileo noticed this and found it disturbing enough to conclude that concepts like more, fewer, and equal simply don't apply to infinite collections. You can't say whether infinity is larger or smaller than another infinity, because infinite quantities don't obey the comparisons that work for finite ones. He abandoned the question. Georg Cantor, 2.5 centuries later, embraced the paradox and built an entire mathematics of infinity from it. He showed that the natural numbers and the perfect squares really do have the same cardinality, the same infinite size, in a precise mathematical sense. He also showed that not all infinities are equal. The set of real numbers is strictly larger than the set of natural numbers, in the sense that no one-to-one pairing between them can be complete. Cantor proved this with a diagonal argument. Assume you have a complete list of all real numbers. He showed how to construct a real number that differs from the first item in the list in its first decimal place, from the second in its second decimal place, and so on. This constructed number differs from every item on the supposed complete list in at least one decimal place, so the list was not complete. No complete list of real numbers exists. The real numbers are uncountably infinite, while the natural numbers are countably infinite. The infinity of the real numbers is strictly larger. This was deeply controversial at the time. Many mathematicians resisted Cantor's results as absurd or wrong. The idea that there could be different sizes of infinity, and that some infinities were larger than others, struck many as incoherent. Henri Poincaré called Cantor's theory a disease from which mathematics would eventually recover. Kronecker called Cantor a corrupter of youth. Mathematics eventually accepted Cantor. His theory of transfinite numbers is now standard. But the paradox he solved by building a new mathematics pointed at something real. Infinity is not a single thing. There are more real numbers than natural numbers, in a precise, proven sense. The collection of mathematical truths is larger than the collection of provable mathematical truths in any given formal system. Some infinities are bigger than others, and the hierarchy of infinities extends without end. If you can match everything in two collections without any leftovers, and one collection is a proper part of the other, what does the word size mean? The implications of Cantor's diagonal argument extend beyond the comparison of natural numbers and real numbers. The same technique shows that the set of all subsets of any set is strictly larger than the set itself. Apply this to the set of all sets and you get an infinite hierarchy of infinities, each strictly larger than the one before. Cantor called these transfinite cardinals and worked out the arithmetic of operating with them. The first transfinite cardinal, the size of the natural numbers, he called Aleph null. The set of real numbers has a larger cardinality, but whether it's the very next size above Aleph null, or whether there are infinities between the naturals and the reals became one of the most famous open problems in mathematics. Cantor believed there were no infinities between the two. He called this the continuum hypothesis. Kurt Gödel showed in 1940 that the continuum hypothesis can't be disproved from the standard axioms of set theory. Paul Cohen showed in 1963 that it also can't be proved. The continuum hypothesis is independent of the axioms. You can add it to the axioms or add its negation, and you get two different but equally consistent mathematics. This is philosophically profound. Whether there are infinities between the naturals and the reals is a genuine mathematical question, with a determinate answer in some sense, and yet it cannot be resolved by any proof from the standard foundations of mathematics. Either the question has no determinate answer, or mathematics needs stronger axioms than we currently use to settle it. Galileo stopped at the paradox. Cantor built a cathedral from it. The paradox revealed something real and deep about the structure of infinite collections. And the cathedral turned out to contain rooms that can't be entered from its standard foundation. Can two collections have the same size when one is a proper part of the other? And what does size mean in a world where the answer might be yes? The Thomson lamp paradox. Imagine a lamp with a toggle switch. At exactly 1 minute before midnight, you turn it on. At 30 seconds before midnight, you turn it off. At 15 seconds, on. At 7.5 seconds, off. And so on. Each interval exactly half the previous one. By midnight, you've completed an infinite number of toggles, because the intervals keep halving and they add up to exactly 1 minute. Is the lamp on or off at midnight? James Thomson proposed this thought experiment in 1954 to probe the concept of supertasks, the performance of infinitely many operations in a finite time. The task is mathematically legitimate, in the sense that the infinite sum of the intervals, 1/2 plus 1/4 plus 1/8 and so on, converges to 1 minute. The math says it can be done. But what state is the lamp in when it's done? The toggle sequence ends in neither on nor off because there's no final toggle. Every toggle is followed by another toggle. The sequence has no last term, so there's no state the lamp is definitively in at midnight, not from the sequence itself. The sequence doesn't determine the midnight state. This means completing a supertask doesn't necessarily produce a final state. You can do infinitely many things in finite time and arrive somewhere that isn't determined by what you did. The lamp has been toggled infinitely many times, but infinity has no last term, so there's no terminal state the toggles converge to. The question of whether the lamp is on or off at midnight is underdetermined. Some philosophers argue that Thomson's paradox shows supertasks are physically impossible. The lamp can't be toggled infinitely many times in finite time because the physical processes involved, electrical switching, require finite minimum durations. Below some threshold, quantum effects become relevant, and the classical picture of on and off breaks down. Real physical systems don't permit the idealized supertask. Others argue that the paradox shows something more interesting. The mathematics of infinite series doesn't automatically translate into coherent physical scenarios. The mathematical sum of the intervals converges. The physical process of completing the task is incoherent. The gap between mathematical description and physical realization can be unbridgeable. Paul Benacerraf argued in 1962 that there's nothing paradoxical about supertasks in principle, only about expecting them to have determinate outcomes. If you complete infinitely many steps, why should the result be determined by those steps alone, rather than by additional information about the state of the system? The lamp's midnight state might simply be underdetermined by the history, and that's fine. Not every physical question has to have a unique answer determined by prior history. Whether real physics permits supertasks or forbids them, and whether the answer matters philosophically, depends on views about the relationship between mathematics and physical possibility that remain contested. After infinitely many changes, what is the state of something that was never allowed to rest? In certain spacetimes permitted by general relativity, including some models of the interior of black holes, the causal structure allows for infinitely many events to occur in a finite subjective time. Whether these models are physically realizable or mathematical artifacts is contested. But they show supertasks aren't obviously impossible in all physically conceivable scenarios. Max Black proposed a related marble transporter puzzle, where two machines alternate, transferring a marble infinitely many times in finite time. Like the lamp, there's no last step that determines the final state. Unlike the lamp, the marble has to be somewhere. Whether this shows marble transporters are impossible, or that physical location can be undetermined after a supertask, depends on prior commitments about determinism. What's clear is that the lamp and the marble transporter both probe a region where mathematics is more confident than physics. The mathematics of convergent series is clean. The physics of completing infinite tasks in finite time is not. After infinitely many changes, what state is a thing in when none of its changes determine the final state? There's also a question about what the lamp problem reveals about the nature of infinite processes in time. Physical processes have states. At every moment, a physical system is in some state. If you complete an infinite task, the system must be in some state afterward. If the infinite task doesn't determine that state, something else must. What is the something else? In some formulations of the Thomson lamp paradox, the state at midnight is simply stipulated to be part of the setup. You decide separately what the lamp's state is at midnight. The infinite task and the midnight state are logically independent. This might seem like a resolution, but it's also a concession. If the infinite task doesn't determine the final state, then the task alone doesn't constitute a complete physical description. Extra information is needed, and where that extra information comes from is unclear. The lamp at midnight is neither on nor off by the logic of the sequence. What is it then? What's clear is that the mathematics of convergent series is clean, and the physics of completing infinite tasks in finite time is not. After infinite changes, what state is a thing in? Achilles and the tortoise. Achilles is the fastest runner in the world. He gives the tortoise a head start of 100 meters and begins to chase it. By the time Achilles reaches where the tortoise started, the tortoise has moved forward. By the time Achilles reaches where the tortoise was, the tortoise has moved again. Each time Achilles closes the gap, the tortoise has advanced. There are always infinitely many gaps to close, so Achilles can never catch the tortoise. Zeno of Elea proposed this argument around 450 BCE, and it was not intended as a claim about slow tortoises. It was a philosophical argument against the possibility of motion itself, or at minimum against the coherence of a picture of space and time as infinitely divisible. If space can always be subdivided, and if every act of motion requires traversing infinitely many subdivisions, and if completing infinitely many tasks is impossible, then motion is impossible. And yet things move. Something is wrong with the picture. The mathematical resolution came with the calculus and the theory of infinite series. The sum of infinitely many terms can be finite. 1/2 plus 1/4 plus 1/8 and so on converges to 1. Achilles covers the first gap in some time, the next gap in half that time, the next in half again, and the sum of all those times is finite. He overtakes the tortoise at a finite, computable moment. This resolution is mathematically sound. Whether it's philosophically satisfying depends on what you think the paradox is really about. Zeno's argument assumes that an infinite sum of times is necessarily infinite, because there are infinitely many terms. The mathematical resolution shows that this assumption is wrong. Infinite sums can be finite, but accepting this requires accepting the coherence of completed infinities, of finishing an infinite process. Aristotle, working without calculus, distinguished potential infinity from actual infinity, and argued that only potential infinity is real. You can always add one more to a series, but you can never have an actually completed infinite series. Whether completed infinities are real or only potential is a question in the philosophy of mathematics that predates Zeno and postdates Cantor. Mathematical practice treats completed infinities as standard. Whether the mathematical objects correspond to physical reality is a separate question. The deeper Zeno problem is about the structure of space and time. If space is a continuum, infinitely divisible with no smallest unit, then motion through any finite distance traverses infinitely many points. Whether that traversal constitutes an infinite task that needs to be completed, or whether it's just a mathematical description of what motion is, depends on how you interpret the relationship between mathematics and physics. Modern physics doesn't definitively resolve this. Space might be quantized at the Planck scale, about 10 to the minus 35 meters. If so, space isn't actually infinitely divisible, and Zeno's argument doesn't get started. But we don't know whether the Planck scale represents a genuine discreteness or just the limits of our current theoretical framework. Achilles caught the tortoise. Nobody disputes this. The question of why remains subtler than it looks. If every journey is made of infinitely many steps, what exactly happens when you finish one? The Achilles, Dichotomy, and Arrow paradoxes form a family of arguments that attack motion from different angles. The mathematical resolutions are real and powerful, but they work by changing the mathematical framework rather than directly addressing the philosophical worry. Calculus says you can sum infinitely many terms to get a finite result. Zeno would ask what it means to sum infinitely many things. If you perform an infinite number of additions, you've done infinitely many things. And Zeno's original worry was that doing infinitely many things in finite time is impossible. The calculus doesn't address this worry. It provides a mathematical framework in which the worry doesn't arise because the infinitely many additions are defined as a limit rather than as an actual procedure. Whether a limit is the right way to think about physical motion, or whether it's a convenient abstraction that avoids the philosophical question, is something physicists and philosophers don't fully agree on. Physics holds that calculus describes reality well enough for all practical purposes, and that philosophical questions about correspondence are less important than getting the calculations right. The philosophical questions don't disappear just because the calculations work. They sit there, in the gap between mathematical description and physical reality, pointing at something that hasn't been fully articulated. Zeno got this right. Motion is philosophically strange. Things move, the world changes, there's a difference between here and there. Zeno's paradoxes articulate what's strange about motion by constructing arguments that make it seem impossible. The arguments fail, but they fail in ways that tell you something. Achilles caught the tortoise. The catching took a finite time. That finite time contained infinitely many subintervals. All of them were traversed. Whatever that means is still being worked out. What is the nature of a process that's made of infinitely many parts but takes finite time to complete? Zeno's dichotomy. Paradox. Before you can walk to the door, you must first walk halfway there. Before you can walk halfway there, you must first walk a quarter of the way. Before that, an eighth. And before any step you take, there's always a prior halfway point you haven't yet reached. To begin walking, you must complete an infinite number of prior tasks. But completing an infinite number of tasks is impossible, therefore you cannot begin to walk. This version of Zeno's argument attacks the beginning of motion rather than the catching of a tortoise. The previous paradox about Achilles showed you couldn't finish an infinite series of tasks to complete a journey. This one shows you can't start either. Every first step requires a prior step, which requires a prior step, with no first step available. Aristotle called these arguments puzzles rather than proofs, because the conclusion contradicts experience in a way that's too obvious to be accepted. Things do move, you do walk to the door. Whatever is wrong with the argument, the conclusion is certainly false. But identifying exactly what's wrong has been contested for 2.5 millennia. The mathematical resolution handles the original Achilles paradox more cleanly than this one. The Achilles paradox has a convergent series with a finite sum. The Dichotomy Paradox asks about the beginning of a series that has no first term. You don't start with the halfway point and work your way down. You start at the beginning and work your way forward. But before the beginning, there's always another halfway point. One response says the paradox is based on a confusion about the nature of instants. Movement through space doesn't require performing a separate act at each mathematical point. The points are abstractions. Motion is continuous, and a continuous process doesn't need to be passed into discrete steps. Zeno's argument presupposes that motion is a sequence of discrete steps, one for each mathematical point traversed, but that presupposition is false. Motion is what happens between the points. This response is philosophically attractive, but philosophically incomplete. It says motion isn't a sequence of discrete acts without explaining what it is instead. Mathematical physics models motion as a continuous function, mapping time to position, but continuous functions don't explain away the puzzle of how a continuous process gets started any better than discrete steps do. Another response accepts that the dichotomy series has no first term and says that's fine. A convergent series can be summed even without a first term in the relevant sense, because the sum is defined by the limit of partial sums rather than by a first step. Starting to move isn't performing the first of infinitely many steps, it's engaging in a process that, described mathematically, has a certain structure. Whether this dissolves the paradox or talks around it is something philosophers and mathematicians have disagreed about since Leibniz and Newton gave them the mathematical tools to try. The door is right there. The infinite halvings between here and there are real. What makes it possible to arrive? The dichotomy paradox has a companion problem about where exactly motion begins. When you start walking, at what instant do you transition from being at rest to being in motion? There must be a first instant at which you're moving rather than stationary. But at any proposed first instant of motion, you could ask about the instant immediately before it, when you were presumably still at rest. If there's no smallest positive interval, if time is continuous, then there's no sharp boundary between rest and motion. The transition is a continuous event without a first moment. This makes rest and motion seem like they blend into each other at the boundary, which contradicts the clean distinction we normally assume between them. Classical physics handles this through differential equations that describe the trajectory as a smooth curve, but doesn't specify what happens at the microscopic level of the transition. Quantum mechanics adds another layer. The uncertainty principle means that position and momentum can't both be precisely defined at the same instant. An object with a precise velocity has an uncertain position, and vice versa. The classical picture of an object at a precise location with a precise velocity, which Zeno's arrow assumed, is already ruled out by quantum mechanics. An arrow in flight doesn't have a precise trajectory in the quantum sense. It has a wave function that spreads over many possible positions and momenta. Whether this dissolves Zeno's paradoxes or just replaces them with quantum mechanical versions is a matter of perspective. Quantum mechanics doesn't make motion more intuitive, it makes it stranger. The arrow doesn't have a definite position at any moment. Its position is given by a probability distribution. The paradox of how something can be in motion when it has no definite trajectory is, if anything, sharper in quantum mechanics than in classical mechanics. Zeno asked about an instant. Quantum mechanics says instants don't have the properties Zeno assumed they would. That's a kind of resolution. It's also a kind of deepening. If you can never pinpoint the first moment something starts moving, what does that tell you about the nature of change? The arrow paradox. Imagine an arrow in flight. At any single instant of time, the arrow occupies a specific region of space. It's in exactly one place. During that instant, it hasn't moved. It's perfectly still. If you take a photograph with an infinitely fast shutter, the arrow is at rest in the image. Now consider the arrow's entire flight as composed of such instants. At every instant, the arrow is at rest. If the arrow is at rest at every instant, and if time is made entirely of instants, when does the arrow move? This is Zeno's arrow paradox, the most conceptually precise of his 4 arguments against motion. The others focus on infinite divisibility of space and the impossibility of completing infinite series. This one asks about motion itself at an instant, and the answer is disturbing. At any instant, there is no motion. Motion requires a change of position over a period of time. An instant has no duration. There can be no change during a durationless moment. So at every instant, the arrow is motionless, and yet it's flying. The standard mathematical response says that motion at an instant is defined by the derivative, the instantaneous rate of change. Calculus gives you velocity at a point, which is defined as the limit of the average velocity over shorter and shorter intervals, as those intervals approach zero. The arrow at an instant has a velocity even though it's not moving at that instant in any finite sense. This is mathematically rigorous and practically powerful. Newton and Leibniz built classical mechanics on it. Every calculation involving velocity or acceleration uses exactly this definition. It works. But whether it philosophically resolves the paradox depends on what you think instantaneous velocity is. It's defined as a limit, a mathematical construction involving behavior over intervals, not behavior at the instant itself. Whether the arrow at an instant really has a property called instantaneous velocity, or whether velocity is fundamentally an interval property that we've learned to discuss using point language, is a philosophical question calculus doesn't answer. Bertrand Russell proposed a static theory of motion. Motion, he said, is nothing but the arrow being at different positions at different times. There's no intrinsic property of being in motion. At every instant, the arrow is simply where it is. The appearance of motion is just the arrow being at different places as time passes. There's nothing more to motion than that. Aristotle's response was different. He denied that time is made of instants the way Zeno assumed. Instants are limits, not parts of time. Time is not composed of durationless moments, any more than a line is composed of durationless points. Points are boundaries of segments, not building blocks of lines. Similarly, instants are boundaries of intervals, not building blocks of time. If time has no smallest parts, the arrow paradox doesn't get traction. Modern physics is ambiguous here. Quantum mechanics doesn't define position and momentum at a single instant simultaneously, so the picture of an arrow at rest at an instant is already strained. Whether space-time is fundamentally continuous or discrete at the Planck scale is unknown. If it's discrete, then there are no true instants, and Zeno's argument has a false premise. If it's continuous, the argument's premise is real, and the question of what motion is at a point remains open. The arrow is in flight. At every moment, it's somewhere. Between being here and being there, something happens that isn't fully captured by either location. What is the thing that makes now different from stopped? Aristotle's response, that motion is a continuous process rather than a series of discrete states, is still common. But if motion is continuous change with no smallest parts, the question of what motion is at an instant requires defining instantaneous velocity, which brings back the derivative and all its philosophical baggage. The derivative works. It's the right tool for describing motion in classical mechanics. What it doesn't provide is a picture of what motion is, as distinct from a description of how to calculate with it. Physics describes motion mathematically with extraordinary precision. The philosophical question of what motion is at the most fundamental level remains open. Process philosophers following Whitehead argue that the right ontology inverts the usual assumption. The world is made of processes and events, and the abstraction of a thing at an instant is a useful fiction extracted from the more fundamental reality of process. On this view, the arrow paradox dissolves because the arrow is not an object at an instant that somehow also happens to be in motion. The arrow is a process of flying, and any moment you extract from that process inherits the flying from the process, rather than having motion as a separate property added to static position. Whether this is right is a matter of deep philosophical disagreement. It's also a disagreement about ontology, about what kinds of things ultimately exist that physics doesn't settle. The arrow is in flight. At every instant it's somewhere. There's something that makes it flying rather than just being at different places at different times, is what the paradox asks for. What is the thing that motion is, when it's not at any of the places it's been?